We are running about 5 minutes behind schedule right now, so don't look at the times on your badge schedule. They're wrong. But don't worry, we'll make it up in the break. And I'd like to announce our next speaker. So online payment systems have a problem because they need to balance speed and security. Srini, the Chief Development Officer at Aerospike, found a way to leverage DRAM and flash storage to create a hybrid memory database that makes things both safe and fast. He's here to share some use cases with us.
Can you hear me? Hello? Okay, good morning. My name is Srini Srinivasan. I am the founder and Chief Development Officer at Aerospike. The previous talk about CosmosDB is kind of a great way to kind of set up some of the work that we've done at Aerospike. Aerospike was founded by myself and my co-founder Brian Bukowski, a networking expert, about 2009. We've been working on this project for almost like 9 years now. And what we will show you are certain trade-offs that we have made, which are a little bit different than what folks at Microsoft have made. I have the greatest respect and for Leslie Lampert, especially, and we use some of his algorithms in our product. I'll talk a little bit about it. What I'm going to really focus on today is to give you an idea of the kinds of extreme use cases that people have been that needs to be solved especially in terms of fraud detection, risk management, etc., for payment systems. And why and how we have used a different kind of database architecture which takes SLAs to a whole new level. One of the things in the previous talk was about SLAs, 99 percentile of latency being less than 10 milliseconds. We at Aerospike actually solve problems where the 99th percentile has to be well under 1 millisecond. So 10 times more extreme in terms of SLA kind of SLAs that we have to achieve. So that's kind of general high-level setting for the talk. Let's talk about some of the use cases and what people are trying to do in this area or have been doing. And these are all the use cases I have here are real deployments. I will not mention any customer names, but these are pretty well-known companies in the world. The business challenge for a large retail bank in terms of risk management, they hit this challenge a couple of years ago. And what actually happened to them was, and I'll talk a little bit about it later, but generally, a relational database becomes very slow when you have to deal with a lot of changes, as well as provide low read latency for a large number of requests. And this is essentially because of the way the data is brought into cache from persistent storage using buffering and so on. There are papers by Mike Stonebreaker on this maybe 10, 15 years ago on why it is that it happens and why a database systems need a rewrite. This was, that is one of the reasons why the NoSQL kind of movement started. It got driven from the internet, where I have some experience. I have some experience in databases as well as in running internet systems. And caching is a very common way to solve such scaling problems. But it came with a bunch of cost. At some point, this particular bank needed to scale it up by about 6x. They were already running with 150 caching servers, and then a hybrid memory architecture ended up with them using less than 10 servers. And it's all about hardware and how you leverage flash and what kind of algorithms you can do to enable real-time access by not really using a lot of DRAM. Another kind of use case is in fraud detection. This is again a very large payment company in the world, and the fraud detection use case here is the business challenge again is very similar. These guys are already at scale. They were using a certain relational database and a caching solution in front of them. And what happened in that case was they again reached about 200 kind of servers. All of the data had to be in memory, in DRAM, and the whole management nightmare of operations came in. They were achieving their SLAs at certain scales that we're in. This was again a few years ago. After which, they were growing explosively. They needed to kind of size the system for 10 times higher. And again, once again, a 200-node cluster got reduced to 20 nodes using this kind of hybrid memory architecture that I'm talking about today. And that's the kind of changes. Again, you need to maintain the same SLAs of a millisecond or so for these requests. So if you look at how these systems are set up, essentially, you have something on the edge, and this is a hybrid memory database. Aerospike is essentially the only one I know of which does it at this extreme level. And essentially, you have a bunch of machine learning and various algorithms in the front edge, which enables these systems to make real-time decisions based on some models. The models themselves are not necessarily computed in the front edge. They're computed using traditional technologies that you know of, like Teradata, Hadoop, HBase, Spark. Pick your favorite kind of analytics algorithms to generate models on lots of data. Feed that into a front edge database, which is based on hybrid memory, and then in real time, you can achieve amazing levels of what I would say throughput with very low latency and high uptime. And again, low latency, heavy write load, 100% uptime, all the things the CosmosDB folks talk about are all applicable in this area. So there are a whole bunch of use cases in this area, even though I'm focusing more on the payment side. So what exactly is the problem? Right? Why do you need 1 million transactions per second database? It is very clear why the CosmosDB folks need it. They're doing a global database, they're kind of replacing something across the world, and of course they're going to have trillions of transactions. But Aerospike also delivers across all our customers trillions of these transactions a day. And some of them run on the cloud, some of them run on Azure even, some of them run on Amazon, many of them run on their own data centers achieving this. So what are these trillions of transactions, which people are doing? Why is it even happening? And this is not actually a competitor. Everything I'm talking about here is not about old relational kind of use cases at all. I'm myself a relational database person. These are completely new use cases driven by the internet use. For example, the Indian internet market is growing like leaps and bounds, and I think it was, about 6 months ago, all the money was sucked out of the system. That was the kind of interesting shock, right? It immediately vaulted India to a leadership space in kind of, what do you call it, in the new kinds of payments. And that's kind of interesting, right? And people like, Paytm, Freecharge and so on, especially Paytm, have become like household names in India because of that. And that's kind of fundamental to some of the things that are going on. Payment, ecosystem has, normally when you go pay with cash, you just go somewhere and you pay cash and you're done. If you're using a Paytm account, you're paying somebody, there's a person who pays, the person who receives the payment, But is that enough? Because payment comes through all kinds of channels, right? So you have people, ordering something on a particular government website, and then there's a simple, a simple model will suggest that you just do some fraud analysis based on just this information. But that's wholly inadequate because, when you're walking around, like for example, sometimes the Wi-Fi here, as soon as everybody showed up, it was really working well in the morning. When everybody showed up, it kind of, there was a little glitch. Some of you might have noticed, right? At that time, if I didn't, I would do my Paytm transaction through the, not through Wi-Fi, through some other, through my carrier network. Now, depending on where the fraud is happening, somebody could have hijacked either the Wi-Fi network or the carrier gateway or whatever it is. You need to be able to figure out where all these transactions are coming from. You can't just focus on the sender or the receiver, and that's kind of fundamentally the point. And then it gets even more complicated. There are a zillion channels through which all of these requests come in. So what is it that you have to track in order to detect fraud in a payment system? You have to really understand and have great visibility into every actor in your network. An actor is not just the person paying and the person receiving the payment. There are like a zillion other actors in terms of intermediate gateways. You can come to a website which is kind of spoofing something on your network. You think you're going to a website, but it's basically you're going to some kind of scaffolding page. And all of that needs to be understood by anybody on the other side. They get all this information through the network. They can actually track it. And that's kind of fundamentally the point. And there are a bunch of companies I've indicated here, but the main thing is all of them have in common basically one thing, which is they want to detect fraud in terms of what's going on in the world, in terms of the network, and they have probably a few number of business transactions per second. We talk about trillions and millions and all of that, but actually the number of people actually in India or for that matter any particular place like North America paying per second is not like a million people are buying things per second and making payments. But in order to kind of detect fraud, keep track of it, you have to not just do reads. You have to keep track of the fact that somebody came in and did make a payment, didn't make a payment. You got to be making a lot of writes. But also for each of that data, you got to look at transaction history on every actor in the system. It could be thousands of basically reads and writes to the database for each business transaction. And there is really mostly the traditional databases simply will not handle it. It will handle it if you would do a lot of work on top of it in order to get the low latency, for example. Because if you can't detect the fraud within seconds, and if you let it go on for hours, you're going to lose a lot of money. You can, of course, correct it later, but the amount of business risk is immense, and you can make all of that go away if you have a database which can handle millions of transactions per second on the edge with very low latency and high uptime. That's fundamentally what a hybrid memory architecture allows you to do. I just want to say a couple of words here on the actual India market. I'm speaking in Bangalore. I've been observing this market. I've been visiting like maybe every 3 months for almost like 15 years. I work in technology and basically in these kinds of areas. And what I'm seeing here is not any different than what I saw earlier in the US and what happened in China maybe 10 years ago. So all these companies, right, they're just not going to be household names right now. They're going to be immensely profitable because they have to execute on all that. They're going to be huge global companies like, like all of the whole Alibaba kind of system that China has thrown out. There's going to be like many such things coming out of India, right? And the scale is only going to increase. It's going to double. If you think trillions a day is enough today, you're going to need like 10 trillion within probably a few years. Okay? So that's kind of how this market is evolving, and I think that's actually a great opportunity for the kind of work that the CosmosDB folks are doing, as well as what we are doing, to kind of help companies reach there. There's also another interesting thing. There's a whole thing about, we can just solve all these real-time problems using a streaming system. It is true that you can do really sophisticated things with a streaming system, but when you have a very sparse database, in the sense that you have, India has 1 billion people, each of them has, let's say, at some point will have like, everybody's going to have a device after the Reliance Jio announcement. It's all going to be smartphones. So what will happen is, they'll get 2. Why will they stop at 1? So you will end up having like 10 to 20 billion things you have to kind of store in your database. Try running that on MySQL, right? It's not designed for that. And that's okay. There's nothing wrong with that. But when you want to actually access the 100,000 of these 10 billion things that are on your website at a particular amount of time, a streaming solution is brilliant. Even 1 million or so, it'll handle really well. But if you want to have all the history for these million objects over the last 4 months, each of them you're going to get 100 or 2,000 more objects. You can't store the 20 billion objects as well as all the history in DRAM and actually build one of these, all the startups I talked about, right? They need to be able to solve the problem today. They can actually solve it by using a database which can do a very good index join, on these data and still achieve that at a fraction of the cost they would have to do if they had to store all of it in memory. And that's actually game-changing for many of the smaller players, because that will give somebody like ATM the wherewithal to actually stand up to somebody like Reliance, GeoMoney, and so on. And you're going to see this happen. And of course, they have to all do it all right, but technology is their friend. Okay, disruption in technology is what goes on with Flash and so on, which I'll talk about in a second. So that kind of motivates the general problem here. So what exactly is the work that we have done at Aerospike, right? And again, there was a slide from the previous talk, which is pretty much the same thing I put up here. The only thing is the 99th percentile is less than 1 millisecond instead of 10 milliseconds, and that's okay for the applications they're doing. For us, it's not. For the applications that we are actually focused on, which is a narrow slice of the market, but it's really at the edge, at the most high end of mission critical kind of cases that you could ever care about. It's like a Paytm or a PayPal or like a Visa or Master, pick whatever. None of these. I'm not talking about these as customers. I'm just talking about these as players who have to solve these problems, right? So the one thing I want to point out is I have conspicuously left out so far is consistency. I'll share a few thoughts on that later. But I'm really talking about real deployments that have happened at scale for 8 years is basically topic of this talk. And the future has to have consistency, much like what the speaker earlier talked about. And that's, how much consistency can you get without compromising on the performance I'm talking about here is a fairly sophisticated problem. And so what exactly, is the current architecture with everybody? The traditional architecture here is essentially sticking a cache in front of a database. Okay? There are all kinds of problems with it. First of all, it's very complex. Caches fail. And when they fail, loading them back in creates a huge amount, of issues. And then it takes time. What do you show a user who's coming to your website when some caches fail? The user doesn't care. They could make a trade. They would have made a payment. Their account has changed. They saw the new value. Great. Cache failed. They go to the website again. They see the old value. It freaks them out, right? They're going to come back at the bank and say, hey, you know what? I made the transaction. My money's in the account. Money I can't show. The bank's going to go, oh, don't worry. The cache failed. It's going to come back in an hour. This is not a good user experience. Okay? And I think the government will have regulations against this kind of stuff. And so people could go to jail and so on, right, in some countries for this. So the consistency of the actual view a user sees is extremely important. And caching is extremely limited for these kinds of applications. Heuristically, it works well. Scalability is another issue, as I talked about, right? You have everything in DRAM. If you want to store petabytes or even terabytes of data in DRAM, a company like Big Basket will just not be able to compete today. Right? But they need to compete, and there is a solution which I will talk about. But that's kind of the idea here. What I'm going to talk about is the work that we've done in Aerospike essentially eliminates this dual nature of cache and database, and just takes a database, which is as fast as a cache, in front of the edge, so you don't have to worry about persistence. Okay, because we put everything in Flash. We'll read directly off of Flash. We will use massively parallel architectures to make sure that you can push through 1 million, whatever transaction, we've tested up to like 5 to 10 million per node on a 56-core machine. But really, we can push as much transactions as you can through memory, and we will make sure that there's enough architectural, Flash kind of storage attached to the machine for vertical scaling that you're now able to generate millions of transactions per second using SSDs, okay, at sub-millisecond latencies. What that gives you is essentially very high scale, very low latency, and of course you need a distributed system. It's a given, stable state, Essentially, the other important thing is fast development. I think again the CosmosDB talked about it. So you don't want to kind of have the traditional relational model of making sure that you have to, prefix all the schema. So fast application development is really important. We have a shared nothing architecture in Aerospike. Again, I'm not going to dwell too much on the technology here because the talk's just for 35 minutes. But that's a VLDB paper. You'd expect that by now. We have 2 of them, but read the one from last year. It describes our architecture in gory detail. It talks about how Aerospike achieves the kind of performance I'm talking about here. We use a very specific distributed hash table algorithm with no hotspots, shared nothing architecture. It's a smart cluster. Our client is smart so that it caches some of the mapping so that you're able to scale it very well. Transactions and long-running tasks are to be prioritized in runtime. This is a fundamental point. Whenever a node dies in a distributed system, you have to actually redistribute the data. Redistributing the data sometimes takes a long time. But however, normal transactions have to continue because we're talking about sub-millisecond response time. So we need to have enough copies, we need to be able to continue those transactions while these other things are going in the background like rebalancing. We also, I'll focus less on this. XDR has basically a replication scheme across data centers, so that gives you global distribution. Fundamentally, what you take away from this talk is indexes are in DRAM, data is in SSD. This is a fundamental part, aspect of the hypermemory architecture. And then this results in using parallelism, we can provide extremely predictable performance, very high uptime with low management. Okay. So again, this is actually a repeated thing. I'll move past it. One thing I would like to focus on is I talked about a hypermemory architecture, which is kind of shown on the left of this picture here. We also in Aerospike have a pure in-memory kind of configuration that you can do. What hybrid memory provides, and some of the techniques we use are pretty classic. Log structured file system. We use a copy and write mechanism. We always, it's like more like the group commit that you're familiar with relational databases. Indexes again are in DRAM. It's highly parallelized. You can fit a whole bunch of SSDs onto the node. Okay, and essentially what you can do is in parallel access data directly from disk. So cluster formation essentially is all about Paxos, and this again was invented by Leslie Lamport, who you heard from in the Microsoft talk. Essentially, the idea here is the Paxos is actually an optimal algorithm for consensus in a distributed system in the presence of failures. And that's really important because when you have a cluster which is running, it is possible for any, this is a very simple example here. So where there are 3 nodes trying to form a cluster. Essentially, the basic idea is each of these nodes has to see all of the other nodes. How fast can you kind of come to consensus that the cluster formation is exactly N1, N2, and N3? And we use basically Paxos for it. We only use Paxos for clustering. We do not use Paxos for actual data syncing and so on, because that wouldn't give you the 1 millisecond response time. So when new nodes come in, the nodes go out to do that. In terms of a partition map, the basic idea of Aerospike is we use the RIPEMD 160 algorithm to hash every key, and that provides a 160-bit digest, it's 20 bytes, and we take 12 bits of it to create a 4K partition list set, so to speak. So given a key, given a key space, it is split into 4096 partitions. Now each of those partitions, think of it as a divide and conquer algorithm. Each of those partitions are mapped to nodes, and then you have a mapping of partitions to nodes with first copy, second copy, and third copy, and so on. So if you have 2 copies, there will be 2 columns in this mapping table. And this mapping table is computed based on the original thing I showed of the cluster list, which Paxos kind of allows you to do. One of the things that we do with our partition mapping is that I want you to focus on the second line here, partition P2. There's a whole algorithm. Again, this is in the VLDB paper. You can look at it. We also have all of the code out there in our open source version. So everything I talk about here is actually implemented, and more of it is implemented in the enterprise version. But the community edition essentially has all of these things. So you can download it and try it out at your convenience. So if you take the second thing, the way our partition map works, we have assigned all of this in random. What that allows you to do, but also we preserve the order. So when the node, what the portion of the picture shows here at level B is that N5 has gone down. If you notice, N5 just removed from this, and the rest of the nodes are the same list. Because we are showing 3 copies here, so N3, which did not have a copy of partition 2, will now get a copy of partition 2. And when P5 comes back up, it will reinsert itself in the same place. This is a way to reduce the amount of migrations you do when nodes come in and out of the cluster. We already talked about Paxos and how the gossip protocol is used to figure out a new organization of the cluster. I'll skip past that. Here's an important thing to know. So massively parallel architecture is important because what we do is, in Aerospike is, we can take data and we kind of shard it across, or cluster it across nodes. But within each node, we can do it across disks. So in this particular case, we have like 5 disks per node, and then we have 4 nodes. So it's a 20-way split of the actual data, which means you have 20 SSDs which can be read directly, which is kind of gives you a limit on the throughput that you can actually achieve. Writes are synchronous within a cluster. Reads can go to any, reads are simpler, just go to anything. And all of this has to complete within 1 millisecond. That's kind of, and then we can do much less than that. But that depends on your hardware. If you're on a cloud provider, it'll be a little slower. If you're on your, it'll maybe like 0.5 milliseconds. But if you're on your own bare metal, fully tuned, it'll be like 0.2 milliseconds. So those are the kinds of things that you can achieve. I think it's just a summary of what we do. I already talked about it. In terms of data correctness, I think we basically focus on returning the latest copy of the data, no matter what's happening in the cluster. The caches, we basically eliminate cache, as I pointed out earlier, and mixed workloads should also be able to run well. In terms of distribution, what Aerospike does is allows asynchronous replication across clusters. So when you deploy Aerospike, you always deploy it essentially with a cluster in every data center, if you will, with an asynchronous replication link between both. You can do two-way replication if you want, or you can do a hot standby. It's basically an option that you have in terms of how you can set up a system. The idea here is, since we are really focused on low latency, if we would straddle a cluster's nodes across a wide area network, we will not be able to preserve the predictable latency which you need. So the trade-off then is, if one of those clusters disappears, you do have a little exposure in terms of the lag that you have between when the first cluster talks to the second cluster. This lag is kind of proportional to the speed of light in some sense, because how far these clusters are determines what the lag is to a large extent. So if you have these clusters, many of our customers run clusters close to each other on the same data center or DR, and it's virtually no lag. So also the other thing is, we have to really focus a lot on high uptime, because all of these systems, they're only useful if essentially the system runs all the time. Okay? And the other thing that we have actually spent a lot of time on, which is hard to go through here, but I think once again you can read the paper, is we spend a lot of time in optimizations in C in terms of how code is written, right? If you look at the traditional databases like Oracle and Sybase and so on, they're all written in C. There's a reason for that. They do their own memory management. We do that. We also work a lot on figuring out how the cores work on these modern architectures, and we make sure that you can do CPU pinning. We can assign the threads to the right cores, and also we have our cache line. Our index entries are exactly 64 bytes, which kind of coincides with the cache line. All of that actually makes a really big difference here. We also, a little bit about the data model, how data is organized. Aerospike is a row-oriented database. So what you have are columns, which we call bins. The bins can have flex schema. It's really a column. So you don't have to fix the schema. And what you can do is various kinds of, types in there. The important ones to point out are lists and maps, as well as GeoJSON. These are ways in which you can run spatial queries on Aerospike, but you can also essentially keep lists and maps, key values, and so on. In terms of, this basically just explains to you how we use MessagePack in terms of the internal format. Again, a lot of Aerospike is all about efficiency. How much can you get out of the hardware? An interesting thing is we work on commodity hardware. So if you're running it on bare metal, we get like really, really great performance. But if you run on cloud, we still get impressive performance, depending on the instance and so on that you use. So it's all about squeezing as much performance as you can out of whatever hardware we are given in order to, for the benefit of the application which is using the database. A little bit about secondary indexes. We allow indexing on the base types, of course, string, integer. We also allow indexing one level on list and map. So the idea in Aerospike is we try to do things which will enable us to keep the performance SLAs. So we do not, whenever you see the features in Aerospike, they will be limited. So hypermemory architecture in this case is enabling us to scale 10x higher, but with 10x cheaper kind of footprint in terms of TCO. So when we have that kind of requirement, we can't just do any kind of indexing, because some kind of indexing will make the system really slow, not just for that kind of index, but for generally for all access to the database, and you want to stay away from that. So one level deep into So indexing is based on a scatter-gather algorithm. So what that means is it is best for low selectivity indexes. So when you make a request for a secondary index, you want to get a bunch of data back. So that means you can send the query to multiple nodes and get all the data back in parallel. It actually works really well. However, if you're just going to get an email entry back, it'll still work, but there's a little bit of overhead there. So you're better off using the primary index of Aerospike, which is as optimal as you can get. So what exactly does all of this architecture, I've kind of given you an overview of this architecture, what does it help you in actual deployments, right? That's kind of interesting. And that's where the surprising thing comes. This is from a real deployment, which kind of cut over maybe like 18 months ago. So what we have here is the previous system, which was actually missing SLAs. This is like a less than 2 milliseconds probably SLA. They were missing 98.5%. So they were missing 1.5% of, they were only making 98.5. Once they cut over, we were able to make the hybrid memory architecture 99.95%, which means 0.05%. That's 30 times better. You're missing 30 times your request. I mean, that's huge. Why is it huge? Because everything that you're detecting fraud on, if you can't actually detect fraud on, you still continue to complete the transaction. You can't wait. If somebody is transferring money, you transfer. You're not going to like say, oh, you're committing fraud, and then if the fraud algorithm cannot finish in time, tough luck. You deal with it later, in terms of what you're doing. And that is very, very important to understand. Is the improvements you get from the techniques I'm talking about here are not like you're not going to get 30% improvement. You're going to get 10x, 20x. Otherwise, all of this work that I talked about is not really worth it for somebody to deploy. And that's fundamental. And the important thing is you can do all of this, right, with low cost. This is from another actual deployment which went live probably 6 months ago or so. Look at the kind of savings you get. Right? This is the previous one. And the savings are not Aerospike savings, okay? The savings are triggered by Aerospike, and it's all, the savings are simply between the size of your cluster, how much DRAM you put on it, versus you can stick it all in flash with a small amount of things in DRAM, which is basically where you put the index. When you look at it at that level, you're actually taking advantage of the billions of dollars of investment put in by Intel and Samsung and Micron and all of these SSD manufacturers who are driving this cost curve, right? No other database in the world today allows you to drive that, to use that in your application at the levels that we do, which means one of our earliest things about Aerospike was, our earliest slogan was, how do we provide the ability for startups to grow to Google scale without spending the kind of money that they basically, Google would be able to spend. Google spent a lot of money, Google spend. How do you do that? Because startups will have to figure out a way to do that. And essentially, this is how you do that. You produce something which can scale at Google scale at 10 times lower the cost, and we ended up with like 10 companies over the last 8 years who used our technology and grew to $1 billion. And one of them actually is in. So you can see how this thing supercharged an internet economy. It will not supercharge a very staid, slow economy. Enterprise software is great. It works for that. For somebody who wants to take over the world, like like a Paytm or an InMobi, they need to go fast, and they don't have the kind of resources the big players have. But the good news is the resources are produced by Moore's law on the hardware side of this case. A little bit on the various kinds of. So Aerospike is not kind of a technology which is general purpose. We don't go in saying, we are, for example, CosmosDB, it's a general purpose database. We don't compete with that. We don't compete with Oracle, right? What we compete with is we compete for a use case where nothing really works. So if you look at the kinds of replacements we have here, everything is different. Why? Because people go with what they know best, they try to make it work. And then they hit a scale where it doesn't work, and then they need the next level of technology to go to that scale. And that's what Aerospike is. So you wouldn't see Aerospike everywhere. You would see it in the most important critical places where people need to retain their internet customers. We'll be in the front edge of every internet enterprise. Because you would need something like this. If you don't use Aerospike, you would have to build something like this with some level of cost to pay for it. I'm going to close with this. Essentially, what we are trying to say here, right? Aerospike plays in the x-axis is scale, the y-axis is speed. Okay? And then essentially, what Aerospike is trying to do is to keep the cost curve as a scale be a straight line. And hybrid memory allows you to do that. Okay? DRAM does not allow you to do that. You get like 1,000 node cluster, and you sit there trying to scratching your head as how am I going to manage it? You know, and then you have an ops person running around going like, I don't know which node died. I mean, at some point, it needs to be all automatic, and you know, so you need to reduce the complexity of the whole system. And guess what? We got help from all the SSD manufacturers with all the work they've done. These things are getting better. Intel has produced like, you know, Crosspoint. Optane has come out, and they're now running Crosspoint on the memory bus. You can bet that we will continue to work in this project to make sure that all of those benefits appear at the scale level, you know, for the applications. So I think that is essentially. So in closing, I want to say one thing. About when you think about scale, right? You have to think about essentially something which is 5 to 10 years from now, right? I mean, some of these companies, it's not incremental in this case. Some of these things are disruptive, right? Like I use the example of the demonetization, I think, which happened in India. That's disruptive. Now, it is disruptive. You can consider it disruptive in a good way or disruptive in a bad way, right? A disruptive in the sense that that's what disruptive means. It's completely different and it's going to be inconvenient. But what is the gain you're going to get later? Some of the early kind of users of Aerospike and this technology realized that gain. Okay? How did they realize the gain? Because they realized they were a startup. They had to compete with the likes of Google and Facebook and so on. They said, well, if I did exactly what Google has been doing now, I will not be able to win. Now, if you want to win, then here's something which can help for the right kind of use case. That's the way to think about it. You should not apply Aerospike to a system which is going to run, you know, at 5,000 transactions a second. I think any database can do it. But you want to run it when you really care about the low latency, care about the high uptime, and it's a monetary transaction, and you really can't afford to not grow. Those are kinds of the use cases you want to think about for hybrid memory architectures. I think I'm happy to answer questions. I think 5 minutes left.
Well, we have 5 minutes for Q&A. If anybody has a question for Srini.
Yeah, thanks. That was a very interesting talk. This way. Yeah, hi.
Oh, here, okay.
Yeah. So while listening to your talk, I kind of remember a conversation I had with a HFT, high frequency data friend of mine, and he said like all this in-memory thing and horizontal, like general purpose database and in-memory things are cool, but at some point you have to do, what works is like application specific predictive prefetching and things like that. So would you like to comment on that? Like at what point we should think of prefetching and doing your own domain specific, application specific things?
Okay, you would have to do it if you, I would suggest you take your application and try out the hybrid memory architecture, okay? You will find that in the caching architectures, you would find that the prefetching was required in more ways, for more applications than they are needed in this case. We just moved the line where you need to do that. So there are still things like actual stock trading which go in nanoseconds. You won't use Aerospike for that. Right? They put the algorithm on the chip, right? But if it's anything which is millisecond range, sub-millisecond, 200 microseconds, you'll be able to solve it with Aerospike. For those, people used to cache it in the application. You don't have to do that anymore. You just move the bar based on the new technology. That's the way I would think about it. There's one thing I want to add, which I forgot to talk about consistency. And again, the previous talk on CockroachDB made an excellent point, which I actually agree with, that that there's a strong consistency and the eventual consistency, and there are things in between. One of the things, I can't talk about it now, but I will talk about it in more detail later, is we are actually trying to see everything about Aerospike is pushing the envelope, right? How fast can we go? How much can we handle? How low can the cost be for that high scale? We're going to do the same thing with consistency. We want to see how much consistency you can get without losing as little of the performance we've gotten you already. So this is the kind of, hopefully, the talk I can give next year as to how we manage to provide you a consistent solution which is actually also push the envelope, just like we push it in other cases. We're going to push it closer to the speed part. Strong means slow. Strong consistency means slow. Okay? We want to change that. And that's kind of what I can't talk more about it because it's like not shipped yet. I'm focusing on things that are deployed today, but that's coming, okay? And that's, I think, a challenge worth tackling.
So all your indexes are transient. I'm guessing it takes like a couple of minutes to recover the system in case of a power crash.
If you lose the entire cluster, but if you lose the entire cluster, use another cluster, would be my answer. But if we do everything rolling. From day one, Aerospike is all about rolling upgrades. And you shouldn't lose, if you do a one node down and you keep upgrading a cluster, you won't lose any writes, you won't lose any reads, nothing actually will go. And you should be able to get sub-millisecond as you go through. Okay? No. On that node, it may take time, but the rest of the cluster is available to you. So your service will not go down. Nodes go down all the time. Okay? We've run services for almost like, I don't know the exact number of years, September 2010. That service is still running. It has changed all the hardware several times. They've done various things, but not a single downtime on that service. Okay? And that's the kind of experience we've had. We've had some close calls over the years, but we've somehow held on.
We have another question over there.
So my question is in two parts actually. The first part is, a lot of what you're depending on is hybrid memory architectures. So what if I'm on the cloud? Are there offerings from, let's say, AWS which offer hybrid memory? That's my first question. And the associated question is, so what happens if I deploy Cassandra against the same hardware? Will I get an equivalent throughput, or is it about how you've optimized your engine to use that hardware?
Okay. For the first answer, it's very simple, yes. AWS has it, Google has it, Azure has actually very good SSD-based instances. We run on all of them. They're commodity hardware-based. The difference between us and a single cloud solution is we run on all clouds, on all data centers, we run everywhere. We're purely based on the hardware that you run on, and it's commodity. The cloud works, non-cloud works, everything works. And you can have an Aerospike cluster on Azure, talking to an Aerospike cluster in a data center, and an Aerospike cluster on Amazon if you want to reduce the risk. We have enabled that. Okay, the second one on Cassandra, I didn't want to be too kind of salesy in this talk, so I didn't talk about any competition. But we, Cassandra, okay, is, how do I answer that question? Cassandra is really good at scale. Okay? You can't scale better than Cassandra. Like anybody can scale, you can't. Speed is not a focus of the system. So of course, if you set up a speed at scale benchmark with us, we're going to be so much better, right? But that's just by definition. So we have had people switch from large Cassandra clusters to smaller Aerospike clusters. One of those examples I showed was exactly that. But there's nothing bad about it. Cassandra is a great product. I just want to make sure that you use it for the right reason. And if you have the problem that Aerospike actually solves well, we're the best for that kind of problem. And that problem seems to be widely applicable these days, as I showed in the kind of industries we have.
There was another question here, I believe.
More questions?
No?
One here?
All right. You again.
Is this a follow-up of that one?
Okay.
Benchmark against SkylarDB, which is like the next incarnation of
Scylla, yes. Scylla is better than Cassandra. It still has the Cassandra architecture. So there will be limits on the architecture at some point. But if you're running it on a small system, it will be great. At some point, the architecture will get to you. It's all about scale and speed, both of them at the same time.
Are there any other questions? All right, then I'm happy to announce that it is now tea break time. I would like to remind you that you may not have food or beverages in the auditorium, so please enjoy your tea break in the dining area. We will be back here at 11:45. Thanks. insight into the consensus problem.
Thank you. Let me get started. This, of course, it's a great pleasure to be here and talking at the Fifth Elephant, coming back to the conference after some time. So, though my work primarily has been on AI and related deep learning and related stuff in the last year or so, this topic is of interest for me. Of course, this is of great interest to my heart. I did my PhD in distributed systems, so it's a pleasure to look at distributed systems and look at some of the issues that were there. So the inspiration, of course, came from the fact that Google came up with their Spanner, and it was made available in the cloud recently. So just wanted to look at that space and what's happening around data safety and consensus and so on. So the talk is a result of that. So we'll, let me see if this works. Strange. Cool, thank you. Yeah, so just want to bring up some of the old systems which were considered complex systems probably about 10-15 years back. Of course, but these were the monolithic systems of old, and people could actually statically program the behavior of the system, and not much of dynamicity was there, and of course it was mostly stateless kind of systems. So why am I bringing this up is to kind of illustrate and contrast with some of the recent systems. For example, things like TensorFlow, which can be seen as really complex systems, right? Complex distributed systems. So, for instance, TensorFlow, I don't know how many people are aware, but it started as disbelief system about 4 or 5 years back, and the disbelief paper was published by Jeffrey Dean and his folks at Google Brain. And it became a bit of a rage at that time because that was the first time people were talking about distributed deep learning, and it became a good piece of work. So people started looking at it. One of the key things was it had a parameter server which was kind of centralized. There used to be worker nodes on each node which used to connect to the parameter server, stateless worker nodes connecting to a parameter server which had all the state, and all of them running certain computations, for example, a deep learning computation or any of that. So that's how it started. So this was the precursor to TensorFlow. So TensorFlow is the next level of system compared to disbelief and so on. But what's different about it? So it's of course a data flow system. So you have a huge number of data flow systems currently on. So for example, the Microsoft had a Link, which was one of the older data flow systems. Amazon has MXNet. Facebook has Cafe. So I mean, what's really different about TensorFlow? One of the key things is the fact that there are two things which of course are important to note here. So one is that so once a TensorFlow graph is built, for example by the user, then the system kind of prunes and figures out what subgraph to do, and certain computations to be done on subgraphs. So that becomes one thing that is doable is concurrently executing multiple parts of the subgraph and doing computations on the subgraphs. That's one unique part of it. The second is, of course, the fact that most of these data flow systems tend to run as, for example, there is a set of vertices and edges connecting them up. Edges typically are used for flow of data, right? That's why they are called data flow systems. And vertices are typically ones which do certain computations on the data which flows in. Traditionally, data flow systems have always been doing computations on immutable data. So the computations don't modify data that is there on that flows into the vertices. TensorFlow allows mutable data. That's a significant difference because what happens is now the vertices can actually modify the data, and so what does it mean for us? So one of the key things is then the shared state has to be managed. So one thing is it kind of merges state management, right, with the TensorFlow graph execution. So that's one point we need to keep in mind. And of course, there are the complexity of the system arises due to various factors, including the fact that it's distributed. You have the distributed master, which prunes the graph and partitions the graph and distributes it to different parts of the network. Then you had kernel implementations, which are the specific implementations. So there are many kernels. So the data flow has to be executed on specific kernels which the user chooses at that point of time. So that's one layer of complexity. Then of course you have the different devices on which they can execute. You have the GPUs and CPUs and whatnot. One key thing, again contrasting from its predecessor, which was disbelief, is that TensorFlow works on a heterogeneous cluster of nodes. Disbelief used to work on just homogeneous nodes. So that's one, again, key difference. So some of these things we need to keep in mind that TensorFlow, why am I talking about all this and talking about TensorFlow at such level of detail, is to illustrate the fact that this is one of the complex systems that, am I on the mic properly? It's fine, right? Okay. One of the systems which are really complex distributed systems, shared state across a set of nodes, need to solve distributed consensus problem. So such systems need to solve consensus at scale. That's the whole point I was trying to make. So, I mean, just to illustrate the problem, right, we go back to school pretty much, and this is how consensus problems are described in distributed computing classes. So I'm just taking you back to school for a minute, so bear with me. But interestingly, right, so two people who are sitting in their own offices want to meet for coffee. So Bob and Alice. So the only medium of communication, this was older days, so they have only an email that can be sent. The email is sent over a medium which is unreliable. So when Bob sends an email to Alice saying, can we meet for coffee? Bob does not know that Alice got the email, right? And Alice sends an acknowledgement saying, yeah, got it, we will meet. And again, Alice does not know that Bob received the acknowledgement. So the medium is unreliable, so that means messages could be lost, messages could be delayed, they could be delivered after an unbounded period of time. Makes it very complex. So the whole point is, if it is a simple, of course, if you think of it, right, it looks like very trivial problem, and a phone call will solve it, and because the other person knows that, if I say, can we meet for coffee, and she says yes, and because I know she heard me, and so that kind of assumes that the act here, the issue is because of the medium is unreliable, you're not sure if the acknowledgement reached the other person. So just before stepping out, right, again Bob thinks, did Alice receive my acknowledgement? And if he thinks, oh, if she doesn't see the acknowledgement, then she may not come. And again he sends another acknowledgement. And again Alice thinks the same thing. If he doesn't see this acknowledgement, then he may not come. So it goes on. So the whole idea is that what I'm trying to say is that in a purely asynchronous distributed system, in which the medium of communication, which is the network, is unreliable, consensus cannot be achieved. So this is the famous Fisher, Lynch, and Peterson's theorem, which says, or the impossibility result as it's called, which says that in a purely asynchronous distributed system, consensus is impossible to achieve. So, I mean, this looks like a dead end, right? I mean, consensus cannot be achieved, so what should we do? However, it turns out that under certain conditions, right, where from a purely asynchronous system becomes slightly synchronous, and from a completely unreliable medium, the network becomes slightly reliable. So then conditions arise under which consensus is achievable. But this is the broader perspective of the problem. So these are the conditions, right? For example, so one point which we can look at is, so this is a table which tells under what conditions consensus can be achieved in a distributed system. So different things are there. So the way to read it is processors can be synchronous or asynchronous. So that's one part. So asynchronous processors, synchronous processors means that when one processor takes, say, n steps, then it's guaranteed that all the others take at least one step. So that's what is typically called as synchronous processors. If it's asynchronous case, obviously there's no step, so the processors need not take any steps, so there's no movement or liveness is not guaranteed. That's an asynchronous system. Message delivery could be unbounded or bounded. That means that there is a time within which message delivery will be delivered, message will be delivered. If it is unbounded, there's no timeout, so timeouts cannot be used. That's one other aspect of it here. So the message delivery is unbounded or bounded. Then of course you have the communication medium, whether it's broadcast or point to point. So if you see it, right, in an asynchronous system, right, consensus is almost always not achievable. The only exception is here you see, which is that, of course, the other aspect is messages could be ordered or unordered. So in that case, for example, you have an ordered broadcast. So this seems like a bit of, how is it possible to implement broadcast primitive, right, in a purely distributed system? So it turns out that case kind of covers systems which are not really distributed. For example, the parallel architectures and things like that, right, in which case processors may share a common bus. So if the bus is shared, then it's likely that they will be able to implement a broadcast primitive, which is an ordered broadcast. If an ordered broadcast is solvable, consensus is also solvable. So they can be treated as problems which can be which is equivalent, so in the sense that one can be used to solve the other and so on. So that's this case, right, that so in an asynchronous system, only in this case, when it's an ordered broadcast, consensus is achievable. In all the other cases, consensus is not doable if the processors are asynchronous. The interesting cases here are probably about 2 or 3 things which we can look at. And of course, there are certain conditions which, or properties of consensus which are there, so which are given here, so consistency has to be there. That means that the input values, so all agents will agree on the same value, right? And it is a value which one of the agents is actually inputting. That's the condition of validity. And eventually the protocol should terminate. That's a termination condition. All these 3 conditions must be met for any consensus protocol. And of course, the key thing is here, if processors are synchronous, right, and message delivery is bounded, right, consensus is always achievable. So what should the system do in this case to achieve consensus? So use timeouts, because you have a bound within which messages should be delivered. For example, I'll say twice that bound will be a timeout, and if something is not delivered by the time, then I can safely assume that because the network guarantees it's going to be delivered within that time, then I could safely assume that the processor is down. The key thing in most cases is we are not able to distinguish when a processor is down from it's not able to receive the messages. So there is a problem in the network versus the processor is failing. So that distinction if we are not able to make, and that's why consensus is not achievable. But if the processor is synchronous and message delivery is bounded, you are able to do that. Similarly, right, the other case when it's achievable is again, for example, when we saw the other one, right, which is when you have an atomic broadcast, consensus is doable. The last case is when processors are synchronous, message delivery is unbounded, but messages are ordered. But it turns out that in this case, right, it's the protocol is actually so lengthy that it's not of practical use. So essentially, right, there are mostly 2 conditions under which consensus is doable. So of course, one is the ordered broadcast kind of thing. The other is, of course, when processors are synchronous and message delivery is bounded. Then you know for sure you can use a timeout and achieve consensus. Let's move on. So just to recap, right, we of course saw the properties of consensus and the Fisher-Lynch-Peterson impossibility result, which said, right, it's not doable, purely asynchronous is not achievable. And of course, the 3 cases are also given here. And of course, shared memory kind of can be seen as because everybody can read each other's messages, right? So in that case, is consensus easier or not? So that question does arise. But it turns out that it's not so trivial that even in a shared memory case, with reads and writes, it's again pretty difficult to achieve consensus. So you need what are called as primitives. For example, you have a fetch and lock, and fetch and add, and so on. So there are a lot of primitives which help you to achieve consensus even in a shared memory system. And those primitives tend to have consensus numbers, so which means that the consensus number of n means that consensus can be achieved even with n-1 failures. So key thing is to understand that consensus in the presence of failures is what makes it pretty hard. And of course, the other thing we can remember is that so far I've been talking about consensus is mostly what's called as the non-Byzantine consensus. So which means that the or what's called as fail-stop failure. So processors just fail by stopping. There is nothing else malicious the processor going to do. But in the case of Byzantine consensus, which is a much harder problem, processors can actually act maliciously. So in the sense that processors send wrong messages to other nodes. It could send one message to one node and send a different message to a different node. So in all of those cases, it becomes very difficult to achieve consensus. So it's been proven that, for example, in the case of, again, we just extend our, the Bob and Alice parable to 3 and Joanne. All 3 of them want to meet for coffee. And it turns out that, again, if the medium of communication, a conference call would solve the problem, right? You just get on a conference call and say, we'll meet. All of them hear what you're saying, they acknowledge, and then you meet. But if the conference call is not there, which is equivalent to a broadcast kind of mechanism, right? Ordered broadcast kind of mechanism. So in that case, this is doable. But it turns out that you have only point-to-point communication, right? There's no broadcast. Like, you can talk to only one other person on phone, and then in that case, how is consensus doable? So it turns out that in this case, so even if one processor or one person can be malicious in the sense that, for example, Joanne decides to tell Bob that I will come and tells Alice he won't come, right? In that case, right, it's impossible for 3 people to actually achieve consensus. So this is what was a general problem called the Byzantine generals problem, and where of course the problem was that there are generals in a war and trying to attack camp, and some of the generals are malicious and they tend to bring down the protocol. So that's the general result, which is that you need 3n processors, and so you won't be able to achieve consensus even if 1/3 of the processors are malicious. So that's the result. So there are, like we said, right, certain conditions under which consensus is doable, but how are consensus protocols implemented, right? So there are ways of implementing consensus protocols, of course, under certain assumptions. So Paxos is one of the common protocols which achieve or which implement consensus. So one thing is, so Paxos was proposed by Leslie Lamport. So a lot of work here, I tend to refer to Lamport's papers and his work. He's been a seminal contributor to a lot of work in this space. So he wrote a paper called the Part-Time Parliament. So this paper kind of describes the problem in a rather abstract way. Talks about a remote island in Greece called Paxos, in which people, right, contribute as legislators. But the problem is the people are all busy, right? So they tend to do their own businesses, but go to the parliament only when they can and come out. Whenever they have business, they come out. But when they are in parliament, they tend to transact some business. But the key thing is, this model is a distributed system because nodes can fail, right? That means coming out of the network or coming out of parliament, it mimics a real distributed system. So he modeled the whole paradigm around this problem of the parliament of Paxos achieving or tabling any useful info and so on, right? So that is how the whole paper was written, but it turned out that it was not well received and for whatever reasons, but it's actually a beautifully written paper. If people have time, please read it. It's called Part-Time Parliament. It's a wonderful paper. But essentially, right, it talks about the Paxos protocol, right, which was the first time the Paxos was presented. But the point here is Paxos is actually a very complicated protocol, so there were several attempts made to simplify Paxos, then fast Paxos, and so on, right? And many current distributed systems, including Zookeeper of the world, use some variation of Paxos or the other. You have many NoSQLs distribute or many NoSQL systems implementing variations of Paxos, one variation or the other of Paxos. So it is a very, very common protocol. Please keep that in mind. So the protocol works something like this. So you have a set of proposers. Proposers tend to say, this is the value I'm proposing. Do you agree? And send it out to what are called as acceptors, which again you have a set of acceptors. And acceptors tend to make local decisions of their own. They don't need to depend on, there's no global decision maker, but every acceptor makes his own local decision. There's a proposal number each proposer sends out. The number is kind of assumed to be monotonically increasing. There's various ways to achieve that. But yeah, so given that proposals send out those proposals, acceptors tend to look at whatever they are getting and don't accept proposals which come later with a lower proposal number. So that way, right, tends to be progressive, and they send the acceptors send acceptances back, and also send acceptance back to the who are called as readers. So the readers finally figure out that yeah, the all or a majority of acceptors have accepted a certain proposal number, which finally becomes the value that the system accepts, or what's called as learners. So so that's how the Paxos generally works. So this is commonly used protocol for achieving consensus. And of course, the other is what's called as failure detectors. So failure detectors is again a different way of solving the consensus problem. Again, right, if you note very carefully, right, a perfect failure detector is one in which every failed processor is suspected of having been failed or being detected by every other processor. And so again, it turns out that due to the impossibility result, we will see that failure detector can, a perfect failure detector can never be live and accurate, can only be one of the two things, because if it were both, then it would kind of violate the impossibility result of Visual Engine Peterson. So there are different kinds of failure detectors, and so based on two things. One is the completeness and accuracy of, completeness relates to how many of the processors which have failed are actually suspected, right, by others. And accuracy relates to being able to figure out if certain processes have failed, then they are suspected, or if ones which have not failed are not suspected. So that's the accuracy, right? How many of them are actually failing and how many of them are actually suspected. So certain systems also use variations of FDs and implement some of these as well. But of course, Paxos has become quite more common, so you might not see implementations of the failure detectors in commonly used distributed systems of today. So one other thing in this space which we need to keep in mind is, of course, the CAP theorem, which of course was illustrated and given by Eric Brewer first. So what he said was essentially that in a partitioned distributed system, you would not be able to achieve both consistency and availability. So which means that people tend to read it as you have three things, which is partition tolerance, consistency, and availability. You get only two of the three, which okay, of course could also be true, but my reading of it is slightly restricted in the sense that I only look at in the phase of partitions. The trade-off is between consistency and availability. So that's the key trade-off which the CAP theorem talks about. But why are we talking about the CAP theorem here is the fact that most distributed system designers have to keep this in mind when designing. The other aspect is, so if you notice, right, the typically systems are known as AP or CP systems. For example, AP systems are those which sacrifice consistency in the face of a partition and stick to availability. That means that they make it available for reading, but it may not be strictly consistent. So they implement typically eventual consistency or other forms of weaker forms of consistency. Of course, the CP systems are those which sacrifice availability in the face of a partition and tend to keep systems consistent. So the MongoDBs of the world would appear here. So what they would do in the face of a partition is some of the data elements might be not available for a write, but it will only be available for a read. So that's the availability sacrifice they have to make in order to make it consistent. Right? And similarly, right, the other systems, the three extremes, right, you'll have CA systems. The CA systems are the traditional relational stores which tend to achieve both, obviously, consistency and availability, but they don't tolerate partition. So you can't have all three, right? So of course, the idea is that they tend to work in a smaller cluster or typically maybe even on a single node, which tends to give them the, so they don't need to think about partitions, but they don't work, right? Obviously, they're not scalable horizontally and so on, right? So they tend to be CA kind of systems. So the point here is that the while the consistency availability trade-off is one thing, practical distributed system designers need to keep in mind a different kind of trade-off as well, which people are not looking at that much, but which is the consistency and latency trade-off. So see, the partition can be seen as a rare event, right? It's not every day we're going to have a partition of a distributed system. Partition is a worst case network failure, right, where the set of nodes are divided into two, so the two groups cannot communicate with each other, right? That's like a extreme kind of an event. So people tend to forget that in a normal operation of a distributed system, the trade-off is between consistency and latency. Because what happens is, if you want strict consistency, involves, for example, protocols like Paxos or 2PC or whatever, right? So they tend to be time consuming. So latency, consistency is a trade-off people have to keep in mind. The peanut system from Yahoo kind of illustrates that trade-off very beautifully. So what they do is they make the system available for reads, or what we call as tail reads. They just tend to make it available for reads irrespective of consistency. So that's and they make the trade-off mostly irrespective of partitions. That's something we should keep in mind, because most NoSQL systems tend to only talk about cap theorem and tend to say, we do this trade-off for the cap theorem and we trade off consistency, but they are trading off consistency even in the face of a non-partition event, which is actually not necessary. So only in the case of a partition you tend to trade off consistency for availability, right? But yeah, so that decision people are not making. But then the other aspect is, of course, the why exactly is consensus useful? I've been talking about consensus, for so long, but why is it really useful? So, I mean, it just, simple things like commit protocols are based on consensus. So people have to agree that, this is a commit or this is an abort. So simple things like that itself requires consensus. So that's the reason two-phase commits, and then there are three-phase commit protocols. Because two-phase commits, there are certain conditions under which two-phase commits tend to fail. Three-phase commit protocols were proposed. So that's one way of looking at transactions, right? And of course, the key thing is to be able to achieve the asset properties as they are called, right? Atomicity, consistency, isolation, and durability in distributed systems tend to be hard. So a lot of distributed systems tend to trade off one over the other and relax consistency and so on, primarily for cap, or in certain cases it could be a latency consistency trade-off as well, like the peanuts system. So consistency becoming important, so asset properties are important, right? So we tend to go on to the kind of systems which have come up of late, and not very recent, but last few years you see a lot of what are called as NewSQL systems which have come up. So they tend to be horizontally scalable and be able to achieve asset properties as well in a distributed setting. So of course the key thing is to look at is the kind of workloads that have been coming up, and especially the kind of operations that are doable, which is write intensive or read intensive. Then you have simple operations or complex operations. Then you have the different kinds of workloads. The data warehouses tend to be here. They tend to do more of reads, but the OLTP kind of tend to do more of writes to the data store. So the whole point is your traditional stores, the relational stores, what are called as GPTRs. So they tend to do some of these. So they tend to assume it's storage is row-wise. What's the time check? Only 5 minutes. Oh, okay. Okay, so tend to be row stores, and indexing is through B trees, and they tend to use locking for concurrency control. And of course, they have a query optimizer which works, looks at again a row-oriented one, and they use disk for storage and so on. Right? These are the properties, but the NewSQLs of the world, right, tend to have different kinds of properties. For example, as defined by Stonebreaker, right, that they tend to support ACID properties, and they use non-locking concurrency control protocols. They tend to have, of course, it's a shared nothing kind of architecture, so becomes easier to implement the same. And of course, high per node performance they tend to focus on. So we will look at some of these. So as an example, right, for example, one could take the VoltDB, which is one of the interesting NewSQL stores. So tend to be what's called a transsyllitical database. So it's both analytical and transactional. So that's the reason it's called transsyllitical database. So it tends to be able to scale out efficiently, tiered data stores, support streaming data. What I'm going to do is quickly skip through a couple of slides in the interest of time. So one is, of course, the other is Clustrix, which is also an interesting NewSQL store. But we'll go on to Spanner, because Spanner is something of interest because it's recent and also from Google, and the fact that they have made it available on their cloud tends to make me talk about it. So I'm just going to take 5 minutes talking about Spanner. So one key thing in Spanner is that it has what's called as a TrueTime API. The TrueTime API they have implemented with very specific hardware devices. So they have implemented what's called as synchronized clocks. So one of the key things which we saw, right, was that consensus is harder to achieve when the clocks are not synchronized. For example, in a commit protocol, getting a timestamp, global timestamp is very hard. And so that is what the Spanner tries to address by having synchronized clocks. They do clock synchronization, of course, only in their data center. Of course, outside of that, obviously, Spanner cannot be used outside of the Google data center. But so they tend to achieve certain levels of reliability in the network. So they have redundant networking and so on, which helps them. Plus the fact that there are nodes in their data centers which tend to be masters, time masters. So they have Armageddon masters which maintain atomic clocks, right, in this system. They have GPS masters also which maintain GPS clocks. So they have 2 clocks for most nodes in the data center, and they tend to maintain time very accurately. So one key reason Spanner is able to do a lot of this is because it's able to synchronize the clocks. Once the clocks are synchronized, then it's a little easier, for example, to say, okay, there is a timestamp, and the timestamp is global because nodes have synchronized clocks. The error is very, very less. They tend to claim it's less than 10 milliseconds. So that's the key difference. So one thing is which we want to talk about is, of course, the fact that CockroachDB is an open source implementation of Google Spanner. The key difference is that CockroachDB can run on any infrastructure. It does not need Google's infrastructure to run. So what's special about it? So what's the difference then between these two is that the CockroachDB will not have the same clock synchronization that Spanner will have, because of course Spanner runs in Google data centers. They have the physical clocks which tend to keep time fairly accurately. So the key point is, what does it give, for practitioners? So the point is, CockroachDB can only do what's called as linearizability, whereas Spanner can actually achieve serializability, or it's the other way around. So serializability is the lesser condition, which means that it essentially gives the view of the database as if every transaction is operating one after the other. That's serializability. linearizability is a harder one, which says that in addition to doing that, a snapshot read would also be consistent. A snapshot read means that just a point in time I go and look at the state of the database. It should be consistent in the sense that there should not be timestamps which may be inconsistent. So that inconsistency will be there in CockroachDB and it will not be there in Spanner. So Spanner achieves linearizability, which is the harder thing to achieve, and CockroachDB will only be able to achieve serializability, which is okay for most transactions, but if you need point of time read of a database, yeah, I'm going to wrap up in a couple of minutes. So that becomes very hard to do. So, and of course the thing is Spanner does not violate the cap theorem in any way. So cap theorem is inviolable, so there's no way it can violate the cap theorem. But one key thing is people can look at it as a CA system. So consistent unavailable, because Google have made partitions such a rare event because of their infrastructure and so on, right? So partition becomes a very, very rare event. So the availability is so high that it can be seen as an effective CA system. But in theory, right, it's a CP system. So it tends to trade off availability, keep it consistent, but sacrifices availability. But because of its infrastructure and what they've achieved, it's an effective CA system. So which is significant, right? CA system in practice at scale is really hard to get, but that's what is Spanner, effective CA system. So let me kind of wrap up quickly and so won't go into too much details. We don't have much time. So tend to talk about formal verification. Something I wanted to touch on, because one key thing is the ability to verify some of these systems is not so easy. So there are work done in the last few years to look into this, especially verifying the safety properties of distributed systems. People have done some work, so we can look at that. And to quickly wrap up, right? So we started from the consensus problem, then went a little bit into consistency issues, acid properties, looked at cap theorem, what is the significance of cap theorem. Then we came to the NewSQL systems of the world, so which tend to achieve acid properties, at scale. So Spanner is one of the perfect examples. Spanner has certain unique features because of its ability to synchronize clocks. So that does result in a lot of benefits for people. And of course, formal verification is something we couldn't touch upon during the interest of time, but we can look up, the slides will be made available. If you have time for questions, I'll stop right here and wait. We have time for questions, right? Okay, cool.
You have, while talking about TensorFlow, you have mentioned kernel implementations. Okay, so can you put a little more insight in kernel implementation in case of multiple nodes have multiple clusters? When, suppose when more than multiple clients, like Python clients, are connecting in the network, so how the load balancing and query prioritization and object serialization gets place?
We can discuss that offline, because it's probably, I took TensorFlow just to illustrate complexity of distributed systems, but we can talk about that off the shelf, because the focus of the talk is more on distributed systems in general and consensus and so on, right? So we will discuss that. But then the fact that I mentioned that was in the context of the fact that TensorFlow tends to do many things, and which makes it very complex to implement, and the need for a consensus protocol in such a complex system. So that's the context in which I have talked about it, but we can discuss that offline. I don't want to take too much of time on, because it's kind of a digression. So yeah, go ahead.
Yeah, hi, you had mentioned earlier in your talk that there were some systems which were trading off consistency when they didn't need to. Could you give an example maybe of that?
React, for example, right, tends to say that we sacrifice consistency because cap theorem tells us so and so. But even in the face of a non-partition event, partition is a rare event, right? Even in the face of even when there's no partition, they tend to sacrifice consistency, which is surprising, right? Which they should not be doing, but they are doing that. So that's the point I was making, that the consistency latency trade-off becomes very important in that case, but they're not looking at that. So I mean, just the point, yeah.
Do we have another question? There's time for one more. Question over there. Can someone hand a mic over to the man? Matt? There.
So what's the catch here? I mean, if these NoSQL systems do scale as good as NoSQL ones, and they give all the goodness of the traditional SQL ones, then, I mean, basically they'll take over, right? They'll take over both the other categories. So what's the catch?
I think so. My view, in fact, I wrote a blog saying that Spanner and the advent of the NewSQL systems could mean the end of the NoSQL world as we know it.
Not just NoSQL, right? Even the traditional SQL ones.
The traditional SQL ones, they have their own use cases, right? For example, you have smaller data sets on which you need to run more computation, so you tend to go for that. That's a very specialized kind of systems, right? So they might still be there, but the NoSQLs of the world might, they have to be really aware of what's going on, because the fact that Spanner and some of these systems can do ACID transactions at scale is significant, and none of the NoSQLs, most NoSQLs won't be able to do ACID. So the real point there is NoSQLs explicitly prohibit ACID transactions. The NewSQLs tend to allow it, but there is of course a penalty to be paid at scale, and which they allow. So that's really the difference. But you're right. The NoSQLs have to be beware now. Yeah. Don't know if I answered your question, but we can talk. Yeah.
There's also a question and answer session today after lunch at 2:40 with all of the speakers from this morning's database section. So if you can hold your questions till then, I think we're about done. Thank you very much.
Thank you.
How are you guys all feeling? Are you having a good morning? Maybe it's not morning anymore. Before we bring on our next session, I would like to make, again, a couple of announcements. I see some friends up in the balcony. You figured out how to get up there. Congratulations. If we get too full up here, you can use the balcony. It's open. Go through the doors in the back and up the stairs. Another reminder to please fill in your feedback forms. You have paper forms that were on your chairs that cover all the sessions in both the banquet hall and the auditorium for the morning. Or if you prefer to fill them out online, you can use the app to access them. And Lochan is just about ready. Now, if you were in the auditorium first thing this morning, you might have stretched. Some nice meditative breathing and then some stretching. But unfortunately, Lochan had to stop when he got to about here and never stretched the bottom part of your body. So I think he might be doing that for you now.
Don't see any. Okay, awesome. All right, please. I mean, when I walk up on stage, I'd like you guys to stand because it's really obvious. Okay, I don't know about you, but I used to have a desk job. I used to be a web developer for not too long, but I thought I had enough of it, and hence I quit. Anyway, so what I'm doing now is another side story, but let's talk about just the low energy states that we normally dwell in as people who work at the computer, as professionals. Well, let's face it, we don't have much happening for us in terms of the sort of jobs that we work, punched to the screen. Blood's not flowing, posture's bad, breathing's bad, back problems, problems with our hands, problems with our necks, headaches, migraines. We have it all. Right, so again, I'd like you guys to close your eyes, because this is something you need to do more often than not, because you need to be in touch with your body, right? All right, close your eyes then. Let's get back to breathing. Just observe and see how you're feeling. You might be having a lot of thoughts, again, contributing to the stress that you already feel. But I'd like you guys to take the time to clench your body, to tighten it as much as possible. And do it with every part of your body, including your face. So if you look funny doing it, it's cool. Just like squeeze every part of your body. Just squeeze with all the energy that you have, right? Squeeze, squeeze, squeeze. Tighten, 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 tighten. Release. So this state of relaxation is something we don't really know anymore. I think we can all agree. Continue to breathe. Breathe in deeply. Exhale. In. Exhale. Can I just bring your attention to something? Please open your eyes. Alright, so when it comes to breathing, again, this is one of the things that is so natural to us, but yet we have forgotten. What we need to do while breathing in is that there's a particular way to breathe. So when you're breathing in first, as you inhale, your chest comes out first. You breathe in with your chest first. So if you keep like one hand on your chest, another on your belly, if you can, all do that, please. Yes. Alright, so this is a test of what part of your torso you're using to breathe is just take a good, nice inhalation and exhale. See what comes out first. Is it your left hand on your chest or whatever hand is on your chest, or is it your belly? Ideally, when you inhale, you want to breathe from your chest, from your thorax, right? As you inhale. And once that is full, your diaphragm then descends, okay? And when that happens, you give it that much more space to breathe in, okay? And when that happens, you breathe in from your belly, basically, giving it more space. So you don't technically breathe from your belly, you're just giving it more space when you breathe. So you breathe in first, your chest comes out. The next half of the breath, your belly comes out. Okay, and when you inhale this time, when you exhale this time, your chest goes in first, and your belly comes out next. Okay, goes in. Alright, so I want you to consciously do this when you are at work, because it's really important, because we don't move our bodies anymore. I mean, the least we could do is breathe right? Alright, so how much time do we have? We have 5 minutes, okay. So, okay, we stopped at the head in the morning and we'll move to the shoulders right now, our deltoids and our upper arms. So I'd like you guys to bring your hands on your shoulders, like so, okay. Alright, so again, breathing is important here as well. So this really stretches up your shoulders and also your chest, your upper back as well, okay. And your neck is inevitably involved. So I want you guys to, as you breathe out, bring your elbows together as far as it will go. Don't push too hard. Don't stretch to the point of pain. Always stretch to the point of tension. Okay? And as you go down, breathe in. As you come up, continue to breathe in. Breathe out as you come forward. Notice your chest collapsing here. Chest expands. Breathe out. Breathe in. Breathe out. Breathe in. breathe out, breathe in, out. Let's go backwards now. Breathe in, breathe out, breathe in, breathe out, in and out. Okay. Okay, who has back issues here? I can't see many hands. I'm very surprised. Okay, that's good. If you don't have it, you will get it. That's simply how it works in the sort of jobs that we do. So anyway, a good thing to do, which makes me feel stupid when I did it, but I used to sit on an exercise ball, you know, the Swiss balls they have. And the best part about that is that you're always like bobbing, right? So it is a great substitute, I must say. The chairs that you get which have arms, again, they sort of make your shoulders rise, and that's probably not something you want to have. You want to be in a relaxed posture, okay? So also you want to engage your back, you want to engage your abdomen, you want to engage your glutes, and every part of you. The only way you're going to get to do that is if you get a ball to sit. The other option is, okay, let me just show this to you because there's no better way to do this. Okay, so this is a squat, okay? It's one of the most natural positions you can assume. Okay, so I'm sure you've been also seeing like graphics on Facebook talking about the benefits of this that makes you like void completely, your bowels feel exercised and massaged. It's all true. Your back here in this position feels really stretched, and so is every part of your leg that is like posterior. Okay, so this is an awesome position to get into if you have the time. If you don't feel that socially awkward, please do this. Okay? So, whatever time you can find, right? At first, it's incredibly hard. What you can do is probably get like a plank or something of that sort to get into this position here, right? Because most people don't have this flexibility. They've just lost it. But if you see most of the villagers or like indigenous people, they quite naturally sit like this. It's just the most comfortable thing to do. And yeah, I just hope you guys would do that sort of thing. Like I said, the other thing to do would be, if you can stretch, it's great. So try and stretch when you're sitting on your chairs. I wish I could do that, but I guess I can do this. Okay. So when you're here, so you want to keep your back as straight as possible, and on your exhalation, you want to twist, okay? And you don't want to twist your lower back. Your lower back has very little ability to actually twist. It's your upper back that is mostly twisting, okay? And you'll find that when you do this, one half of your lung will collapse, okay? So the other one will breathe in or out completely. And you want to do this and just hold for a bit once you're in that position. As far as you can go, you don't have to push this, okay? Okay, so I have like 10 seconds, so thank you.
There we go. Our last talk in the database and data stores sessions is about which database to choose. How big is your database? How big is your data? Is it growing? Can your database scale? Well, Raghunath, who spoke at the Fifth Elephant in 2013, is back to talk about choosing the right database for your project.
Hey everyone. So I'm here now between you and your lunch, and maybe let's do another session of stretches. No, just kidding. Well, I'm from QFET and Cult, so it comes more naturally. I'm not here for that. I'm here today to talk about, as a practitioner, we're often faced with the choice of what database to choose for building that next system of yours, right? And what I want to share here is essentially learnings from my experiences from 2010 building Aadhaar, then building infrastructure services at Flipkart, and where I work currently, which is QFIT and Health Phase, about building data stores for healthcare, right? So there's a problem with my title, right? It says SQL and NoSQL. That's a very common accepted way of referring to relational and non-relational systems, because SQL just simply says what is the query language that you use, right? It doesn't define a class of systems, and we'll get to that. But in general, so the intent is help make our choices between relational and non-relational, the NewSQL, NoSQL, whatever you want to call it, or whether you need to choose Polyglot data stores to get your job done. So let's start with the landscape. This is again from one of the research outputs. So you see this, the purpose of putting this up is saying that your choice is just way too big, right, between in-premise and hosted systems, and roughly classified between relational, non-relational, grid or caching zones, and some of them being in-premise and let's say hosted. So that really leaves us spoiled for choice. But the harder problem is, with every single vendor out there claiming that their solution is the best for your choice, how do you make that decision of what database to choose? Okay, so let's start off with some very basic ways of how you would start looking at database choices, and this is primarily, my talk is going to be more oriented towards in-premise choices, right, with some things that you can pick even from hosted solutions. So let's start off with some of the over-the-hood or the very obvious considerations that you would make. So first and foremost is the kind of data manipulation language, or the SQL or NoSQL choice that you're trying to make, right? So a query language of SQL, it might seem like that it's something of the last few decades, but trust me, it is very relevant. And why so? Because even Spanner, there's a real recent paper that says how Spanner is becoming a more SQL system, right? So SQL as a querying language of choice is not bad, right? So you want to make your choices of saying, hey, is my data more amenable for SQL-like queries? Now that's one choice that you would make. Or you would say, is it more suitable for a key value style operation, right? Get or put. Or even differently, if you're looking at some kind of a graph querying capabilities. And in my talk today, I'll be able to give you examples of some of these cases from real life where you will see that it is quite relevant and it's quite natural to look for a query language support that you would like to have. And another dimension is to look at bulk processing, both in loading and data export. And this can be for any number of reasons. You're trying to seed your database, you're trying to export the data out, take it somewhere. So it's good to get a first-hand view of saying, is that database choice of yours going to give you bulk data exports or transfers? The next one is asset properties, right? So asset, let's look at 1.0, asset properties. So there are the bunch of properties. What does that mean to database choice, right? So if you look at atomicity, it talks about, can be roughly translated into transaction support. Consistency would talk about ordering, whether you're going to be across, if there is replication, is it across replicas, is it going to be eventually consistent, is it going to be strongly consistent? Data staleness, and also durability talks about how durable is the data and can it survive crashes, right? So now when someone says that it's an ACID 1.0 compliant, then you can say that you get the following properties, or you can expect the following properties from your data store. Now more recently, there's another proposal, or in fact implementation of another set of properties called the ACID 2.0. How many of you have heard of ACID 2.0 here? Right. Now, ACID 2.0 is more about is choice, where typically is a matter of choice when you're trying to achieve scale, and more precisely when you're trying to achieve higher throughput, right? And in an ACID 2.0 system where you say that, hey, data can be across replicas, can be associative, commutative, and the data gets relayed in a manner that's idempotent, and the data nodes themselves are distributed, right? What does this mean? It typically means transaction support is a little limited, and what I mean by this is, if you see in the ACID 1.0 world, you could say that multiple inserts across multiple tables, inserts across multiple tables in a single instance is transactional, right? Versus in a 2.0 world, it is probably limited to saying that inserts only to specific records are transactional. Not saying that there aren't databases that offer that, but typically, right, it means that transaction support is limited. There is a relaxed ordering, right? Now, one of the reasons why Spanner has all this fancy infrastructure for GPS and atomic clocks is just to guarantee ordering. And because they claim that they're a globally consistent data store and you want all replicas to converge and converge in time, right? So with relaxed ordering, you get higher throughput, and that also leads to another type, you can read that up, called CRDTs, which are conflict-free replicated data types, and there is ready support for this in an open source system like React, right? Where those conflicts get thrown up to the application, and the application can then decide how it wants to resolve those conflicts. And at least once delivery guarantee. I very recently read that Kafka supports exactly once delivery semantics. That is very hard, or pretty hard to achieve, right? Just guaranteeing at least once delivery semantics itself is fairly complex, right? And what that means is, with at least once delivery semantics, what you get is mostly eventually consistent data stores, right? And this also can lead to higher availability. So you would start considering 2.0 properties when you're trying to achieve large scale. Otherwise, if the 1.0 properties work well, now that's fine. Moving on. What do you expect in wire protocols, right? So wire protocols, most of them are custom protocols on top of TCP/IP. Some of them work on gRPC, and there are very few that even work on say, HTTP. Not much of a material difference in the choices that you're making, but it's good to be aware of what it is, right? Now, support for popular database protocols, and why is this relevant? So if you look at CockroachDB, they give you support for being used via the Postgres drivers. And this is primarily because so that you're trying to make a shift from Postgres to CockroachDB, you could pretty much seamlessly use it and not make too many changes on your application layer, right? So it is good to be aware, or let's say if I were to consider CockroachDB, I would say that, hey, it supports Postgres and I've been using Postgres, so it's good as a matter of choice as an end user, right? Or for that matter, Memcache, for a few years it has always, Couchbase has been supporting Memcached as a protocol, right? So you could talk to Couchbase at the backend, but using the Memcached protocol. Or for that matter, standard interfaces, right? So in the Java world, JDBC is like a standard, and you have JDBC for all kinds of interface, right? Apache Hive has a JDBC driver. You have, for HBase, you have Phoenix, which gives a JDBC driver. Or if you look at Vitis, how many of you heard of Vitis? Any of the Google, YouTube guys? Okay, so Vitis is a MySQL scaled solution built by YouTube and Google. And we came across this in Flipkart when we were trying to scale MySQL. And this does give you a SQL interface on top of an underlying MySQL-based storage, but what it lacked was a JDBC driver. And while we were in Flipkart, our team built and contributed a JDBC driver for Vitis. So it basically allows you to scale MySQL in premise. So it means that across a number of instances, so if you're trying to build any of your custom sharding solutions, this is another viable option, right? But just a case in point where just building that JDBC support opened it out for wider adoption within our company, where most of our instances were using MySQL, right? So you could say that, okay, it now has a compatible JDBC driver, and you can just shift on to that. So it's good to look for that as well. So on Schema, so I sometimes hear this, right? Like schema is evil, right? My system is not able to scale because it is relational, it is very schema defined, and therefore it's a problem. But the truth is, if you really look at number of systems that really need schema-less backends, you can count them like they're very few, right? So either they're sparse metric, or you're trying to look to build entity value, entity attribute value storage. Like for example, like we started off in Flipkart, our catalog used to be something if you're trying to store, let's say, a diaper and an iPhone 6 on the same catalog system. We started off with an EAV store, but then just that couldn't scale, and then later we built something else, right? So for these kind of systems, arguably you have a need for a schema-less system, and you say that, okay, there are a lot of changes, so frequent changes you would go and use such a schema-less store, right? So I'm here, there might be fans here of document databases like MongoDB, and they would argue that it works very well for this kind of requirement, right? Now, what do you lose if you don't have schema, right? And very interestingly though, I think as of 2017, Mongo has announced support for schemas in their database, right? Why that is so? Because in the absence of schema, understanding the data becomes incredibly hard, and what becomes even worse is you have wrongly typed data going into any of these fields, and then when you're trying to make sense of this data when you're querying, it becomes next to impossible. So you're actually making those you're doing all the hard work when you're querying the data. So schema itself is not bad. You really need to be convinced that if you're going for schemaless, why are you going for schemaless, and be prepared to pay the price for going schemaless. Or there's an in-between path, right? So for the ones which use columnar data stores, they require, and you require column indices, for example, right? So if you look at a database like HBase or let's say Cassandra, they allow you to define indices on top of those column families. Why? Because you're trying to query them, you're trying to make that more efficient. Then this kind of an in-between world where you're trying to optimize on both storage as well as on query. Right? So schema, therefore, is not evil, and it is perfectly okay to expect or look for schema support in the database that you're looking for. The other one, cap theorem, right? I'm sure by now all of us would be aware of what's cap theorem, but there's an interesting point about not taking it in an absolute literal sense, and there's a debate about saying, is CP really achievable or not, and so on. But what I liked is in one of these papers, and those references are there, like I found that it is one good example of a fundamental trade-off between safety and liveness in fault-prone systems. That's exactly what cap theorem is. Right? It's trying to define, when you say safety, it's talking about consistency, and liveness, it's talking about availability, and when you say fault-prone systems, it says that when network partitions can occur. Right? So that's the way to look at it. If you just look at the conjecture that Brewer proposed, it is too simplistic to say one is achievable versus not, and therefore it is like kind of too simplistic at face value. There are enough examples where, anyway, CA is impractical because if you're in a distributed world, if you don't go beyond a single node, then the CA is pretty much non-practical. But cap availability and cap consistency is actually a spectrum, and is never and not binary. And I'll give that as an example, right? So if you look at AP reads and AP writes, now, AP reads there are enough examples, right? So you can say that I have a cache, so long as the entire system is available, it's partition tolerant, and I trade off consistency acceptable. What's a good example of AP writes, right? I've seen one very good example, and probably that affects all of us here is, I've read this, of the number of users who use Uber, and I know there are a bunch of Uber friends here. So I believe they built a system for capturing the writes when you complete a ride, right? When you complete a ride, when you probably swipe and you say that you're completing the ride, what is very, very important is to capture that ride, because the customer is not going to wait, the cab driver is not going to wait. It's very important that you capture the ride, and the ride can go to any copy among the available nodes, and with mechanisms like hinted handoffs, finally the data reaches the eventual state. You may not be able to read the data right away, but the write is super important. So AP itself is, therefore you'll see that in these two examples of a cache scenario versus like a Uber-like example, it is a spectrum, right? And so therefore CAP, even with CAP, you go and critique your data sources to see what is it that matters to you more, right? So it's never a binary, right? And then with that, you define your application trade-offs, right? You validate impact on NFS, latency, and I can give you many examples. Again, if I go back to the Flipkart example, so we have systems where, like even on pricing, well, not so much on pricing, but I think definitely on offers, we chose to have availability over consistency, right? And we built systems for that. And that's perfectly all right. And you will define those trade-offs when you're trying to critique it using CAP. And that also serves as a good starting point for considering, right, polyglot persistence. So what I mean by polyglot persistence is something like this. So this is from Aadhaar. So in 2010, 2012, when we built the system, when we looked at the data here, so there is the raw biometric data, the enrollment data, which is roughly now, I think, at 1 billion enrollments, it's probably about a few petabytes, right? So that needs to be archived for 7 years. So that sits on an NFS, and I'll talk about why an NFS versus an HDFS. So this is like an archive store. The same data first actually comes into HDFS for very high throughput processing. The biometric extracts, so those of you who have used your other authentication, the authentication is happening against HBase. So that data is on HBase. The master Aadhaar data is on MySQL. We have indexes, it's no longer Mongo, so it's a little dated, but that's again MySQL. And then we have a query on top which allows you to do all kinds of searches, albeit in a very secure way on, like if you lose your enrollment slip and somebody doesn't have it, how do you find your Aadhaar record, right? So it's the same data, or rather extracts of it, which sits in a highly polyglot store, and the data progresses through various layers. Another concept here is called CQRS. How many of you have heard of CQRS? Awesome. So it basically means command and query responsibility separation. So which means that, in terms of operations, it's like write and get, read. Yes, obviously operations are separate, but what if your data stores themselves are separate, right? And CQRS essentially promotes that. And a number of systems today exist that allow you to realize this, and I think Lagom, if I'm right, among the more recent frameworks gives you first class support for CQRS. Basically what it says is saying that you have writes going into a data store, and from there those are commands, and there is a continuous update of those changes going into a read store so that you can serve the reads of a completely different infrastructure. And what you're seeing to the right is essentially the system that Flipkart has for its catalog. And this system at peak has served like 10 million reads per second, right? That's the read pipeline, and what you're seeing at the bottom, which is highly replicated, highly distributed clusters sitting on Redis, and with virtual buckets managed by the application layer, while the writes or the whole data that gets stored sits on HBase, Elasticsearch, and gets orchestrated through a write pipeline, along with write repair happening across these clusters. So this is one example of basically using a polyglot store, applying techniques of CQRS, right? So that's another. Another one where, without you having to engineer it yourself, now this is an example of some work that I'm currently doing at CureFit, which is we are trying to build a knowledge graph which will eventually be used for such things like an automated symptom diagnosis system, and which can even can aid the doctor in disease analysis, right? I hate to use the word AI, but this is basically a data-driven diagnosis system with no human intervention. And that talks about first establishing a graph of this sort, which kind of says, hey, you have flu, and flu has conditions like, flu as a condition has symptoms like cold, body ache, headache, and so on, right? So very naturally represented as a graph, And what you're trying to do with this, and we built it, and this uses Titan as its storage, and we chose Titan for multiple reasons, right? One is, it could be backed with Cassandra, and Cassandra, as we know it is an AP system, so very nicely maps with what we're trying to do here. Here, more than the staleness of data, what we care about is availability of data. Works well for single query hops, like what we're trying to do here, which is like once in flu, you're trying to traverse to, let's say, cold or body ache and headache. And for a system like this, you can create very interesting solutions on top. But here, with Titan, the point I was trying to make was, with Titan, the underlying storage, you have a choice of either Cassandra or HBase, and for indexing, it's on Elasticsearch, right? So it's again Polyglot persistence. Under the hood, you didn't make a choice, but it's a case where it isn't a single bundled storage engine. So a couple of other things to look at is performance benchmarks, right? In general, benchmarks by vendors are lies, and more lies, right? Why? Because obviously they have a job to sell their databases, so they'll try to take the most ideal case of databases and then, workloads and try to prove that it's right for them. But I found that independent benchmarks are very useful. Like there was a recent benchmark on graph databases, and somebody proved that if you can actually implement a graph for certain workloads on, let's say, a Postgres without even going towards let's say, a Berkeley DB, or let's say, I think they even picked Neo4j and Titan with Cassandra backend. Those graph queries actually work better with a relational data store as its underlying storage, right? Like Facebook Tau database, for example, it's a graph database built on MySQL. So it does help. You might still make your decision or a choice to go with whatever, right? Like even after reading this report, I would still go with Titan over Cassandra. But why? Because I don't have to build the underlying graph storage layer on top of, let's say, MySQL or Postgres. But it's really good to be aware of these kind of benchmarks and use them in your, in your choices. Operations and maintenance. This is interesting, right? So you look at Facebook with all of their engineering prowess, they didn't go and build a storage layer for Tau, right? They went and built it on top of MySQL. Same with the LinkedIn guys, they built Espresso and built it on top of SQL. And if you look at their engineering blogs, and those posts will show you that, both of them built it on MySQL as a storage engine. And why do they do that? They say, hey, we have expertise managing MySQL as a storage engine. We know what to do when you have to replicate data, when you have to restore data. So we would rather use that to build our storage as the storage engine and then build our whatever layer on top, right? Whether it's a document DB in case of the LinkedIn Espresso, or let's say it's a graph database in case of Facebook. And the other important thing is support. Support, either it's paid or whether it's a community, and community where if it is paid, whether it's single vendor versus multiple vendor, and community, again, the size of the community matters a lot, right? Though you would see that a lot of the databases would claim that they are open source, but the only company supporting it would be the guys who created it, right? But that really doesn't speak too much of a large community backing it. The fourth one is a hosted service, right? So coming to this, so when we chose Titan with Cassandra as a storage, Titan interestingly also has storage implemented on top of DynamoDB, right? And if you were to deploy and operate on AWS, then I already have a service that can be managed by someone else, right? So that's a matter of choice in a public cloud. So it says that, hey, it really works, right? So that's again to look at when you're making the choice. Now from here, we'll move on to some of the under the hood considerations, right? Additional things that you generally look for in addition to what were the fairly obvious things. Now comes the database part, right? So between a relational database and a columnar database, it helps to understand how is data stored internally and in the storage layer. So relational, quite naturally, if you look at it, data is stored where all the data in a row is stored together. So which means if there's going to be a disk seek or transfer, it's going to operate at a record level. Versus in a columnar store, all column data is stored together. And why so? Because when you're trying to do OLAP queries, you're trying to do group by, you're trying to do any of those count and any of those aggregate queries, more suitable for a columnar storage. And that's why very, very likely that you'll see most of your OLAP databases making a choice of using a columnar storage at the underlying layer, right? And it gives better query compression and so on and so forth. It definitely helps to know what is the underlying storage engine or what does the storage layer look like for the database of your choice. It also comes with a few trade-offs, and a case in point, like suppose you're trying to build a data store, like let's say Aadhaar is fine, but if you look at that data, you're trying to retrieve a record at a time. A relational store, because it uses a B-tree kind of a store, is probably more efficient than a columnar data store, for example. Now moving on to document, so we have 4 classes, right? So you have relational, columnar, document, and key value. So document is essentially a subclass of a key value store. Data is organized from a DB to a collection to a document. It sometimes have challenges in optimizing storage, right? Because they don't have a data dictionary, so it becomes rather hard to define how do you optimize it at a storage level. Now comes the key value stores, often RAM based, and you see that with key value stores, if you really start looking deep, how many of them give you high guarantees of data durability? And I wouldn't expect them to give that because they are by design, they're meant to give you very low latency reads, right? You're saying that sub-millisecond or sub-2 millisecond reads, they largely try to keep the data in memory. So which means then when you do a write, it's quite likely that writes get batched and then they get flushed to disk. And if you say replicas, if you're trying to say, hey, I require a key value store, which is going to give me very high durability guarantees, where the durability is down to disk and is also distributed. Then imagine the cost of doing that, right? It has to do an RPC, send the data across nodes, and also do a flush to disk. Most of them, while they do, probably might give you the way to tune that kind of durability. Key value stores are better suited for mostly in-memory read-writes with kind of batched flushes to the disk. So data organization. Now this is another interesting topic where if you look at a number of relational stores, they organize data in more like of a B-tree format. And in more recent times, you'll see a lot of these databases trying to use the log structured format, right? And why log structured format? It is for multiple reasons. It started off as being log structure for having very high throughput writes, like a HBase or a Cassandra. They started off using log structured formats for doing the writes. But interestingly, databases like even RocksDB or LevelDB, right, use a log structured format. The reason being, most of them are built for storage on SSDs. And on SSDs with write amplification and your write cycles that you have, a log structured storage format is better suited and gives you more life as compared to in-place updates that you would probably see in a relational store, right? And log structured also means that your data is mostly keyed by the primary key. So that's why if you see a HBase or a Cassandra, retrieval by the primary key is super easy. Secondary indices, even though they provide that, the lookups aren't just as fast. So we'll talk about that later, but generally it's also good to see that what is the underlying data organization on disk. You'll see more and more recent databases having LSM trees. Next one is on replication and consensus. So replication is, so if you're trying to say that you have a globally replicated, completely consistent database, then it means that you're trying to say that somewhere that the replication is possibly, I don't know, I've not read it in detail, but probably Spanner replication is probably, it is like sync replication versus a number of the databases that we know uses async replication, right? And number of replicas, the number of copies of the data that you have, guaranteed writes, hinted handoffs. So all of these are attributes that if you care to read about mostly the open source databases, the white paper, the engineering blogs about them, you will get to see these common things emerging, right? And it always helps to make sense of the kind of guarantees that you can get from the database. Or whether it's a single master read write. Like for example, HBase achieves consistency by being a single master read write, which means it's a single copy of data always is the read and write. All reads and write just go to that copy, for example, right? On consensus, it's used in leader election, and I know that there's this talk of Paxos. So now on Paxos, if I say how many of us have heard of Paxos? Show of hands, please. How many of us understand Paxos? Not me, right? Incredibly complex as a consensus protocol, and and what you would see is that there are newer protocols like Raft, which are also employed for doing this consensus and leader election. It does help to understand replication. What is the kind of consensus protocol in use? Because you'll see that sometimes because of a wrong choice of a consensus protocol, the database can actually be, can perform very badly or perform very poorly when it comes to the safety guarantees. And if you care to look at it, look at Jepsen tests. Again, show of hands, who's heard of Jepsen tests? It's about, very interesting, just read up Jepsen tests. Probably you'll not sleep that night, right? You might have chosen a database, and if you read the Jepsen test results, you'll see that, oh my God, what did I choose? But the good part is what started off as just a critique of those databases. Today you have a number of databases actually come and claim, saying that my database has basically adhered to all of the Jepsen tests, right? And there are enough examples. Jepsen basically started off by the work of one single guy, Kyle Kingsbury. So look it up and do read about Jepsen test results for the database that you're trying to pick. Running out of time, so you're also trying to look at data export and restore. Like primarily if you have strong RPO and RTO requirements and a DR scenario, look for tools that provide full export versus incremental snapshot, tools for restoring from export, and all these things start to matter when you're looking at very large database sizes, right? Like multiple terabytes of data, you're trying to optimize and you're trying to actually ship data. Like here I had a point about large-scale data migration. So there's a reference of when we did the Flipkart data center migration, we actually took disks in a truck, right? It was the fastest bandwidth throughput that we could ever get for transferring data from point A to point B. Right? So, so it does matter to look at these tools for data transfer and migration, right? Another aspect is the mean time to recovery, which is really the time that you take to, let's say, promote a hot standby to master, let's say in a MySQL scenario. And that, in Bitters as an example, is like a click of a button. You can promote a MySQL standby to a master by the click of a button. Now that says something about how you can manage and keep your operations running, right? So it's good to detect failure and validate and promote to a new master or leader. Cost, disk memory ratios. So going back to an Aadhaar again, we store the data on, we moved out of HDFS and moved to disk because to keep such a large cluster operational, the amount of compute that you would have to dedicate to HDFS is more. So instead it is cheaper to move it to an NFS filer, right? So it's good to look at those examples and the amount of data that you can hold in memory and the kind of addressable ratios that you can have. Now power consumption, you'll see that in very large data centers when they say that we'll give you SSD disks, they're actually doing themselves a favor because it's more power efficient to run SSDs than to run spinning disks, right? And if you look at Glacier Store, and there are some references there, very, very interesting, like the Facebook, the way they store photos. Not all disks in the rack are even powered up, right? They try to optimize that because it's super critical when you're trying to create such large, dense storage. Last one is on to look for some DB-specific optimizations. If you really see, you're trying to look at how effectively can you use memory and reduce access to disk or optimize access to disk, right? So if you look at memory, so it all translates to data blocks or block cache, buffer pools. There are enough guidelines around how much buffer pool size you want to give to a MySQL instance, or in case of HBase, like what is the size of the block cache, because primarily it reduces disk I/O, provides lower latency reads, and also potentially lower latency because of high data locality of reference, right? There are a few references to go read up more on that, but effectively what you're trying to do is try to keep data and optimize for keeping data in memory as much as possible and not hit disk. And if you do have to hit disk, techniques like Bloom filters, right, saying which of those data blocks actually contain the data. Either you have indexes or you have optimistic data structures like Bloom filters, which again tell you that, hey, there's a good possibility that this data exists in this block, but it can be, you can get a false positive but never a false negative, right? So these kind of optimizations, and if you read again about databases, they'll say that there is support for, let's say in HBase, support for Bloom filters at a column family level, right? And you know why that is for. They're just trying to optimize on the disk seek and the data blocks that you have to read. So that's just a couple of things, but in essence what it means is the kind of levers that you have in order to minimize the access to disk, and specifically disk seek times more than transfer, and the kind of levers that you can employ as an end user. And that actually takes me to the end of this. Definitely not a comprehensive list, but a bunch of things that you can look at both over the hood and under the hood when you make your next database choice. Some references, it's there all over the talk, so interesting reads. If you go and start looking into each one of them, you'll be able to relate to the various topics that I've covered in the last 30 minutes. So with that, I'm done. Open to any questions.
Questions and answers. If anybody has a question, please raise your hand, and we'll get you a mic. Wow, it's an entire auditorium without a single question. Oh wait, there's a question right
Hello.
Just people are hungry.
It's almost lunchtime. You can almost leave.
Hi. Hello. Check. At the last here.
Oh, yeah.
Can you hear me?
Yeah, I can.
Okay. So I just have one question, or I don't know, more like a feedback that I want to ask or give. So at one point you talked about LSM structures, right? And you said we prefer LSM for the better lifetime of SSDs because compare that to like in-point updates.
In-place updates.
In-place updates. Can you explain how exactly that happens? I mean, because with LSM you generally have a process that comes along with it called the process of compaction, where you end up rewriting the files by taking deltas over again. Whereas in-place updates is all about doing random writes.
Yeah, so random writes actually results in write amplification, right? Whereas when you do the compaction the way you describe it in an LSM, it writes larger blocks, so the write amplification is significantly reduced.
The Paxos protocol we are talking about, and where you said Raft and Zab are also, maybe you might have listed as 3 protocols, but Raft and Zab are just variations of Paxos, so we just need to keep that in mind. Sure. So Raft is just a way to simplify Paxos. And
yeah, I just as an end user found it a lot more easier to even make an attempt understanding Raft. Paxos, maybe, I don't know, it's so incredibly hard.
Sure.
But the point more was to see what is the strength of the replication protocol. So if a database were to come and tell me that they use Paxos for both redirection and replication, I know that those guys have done some very serious engineering work, right? Whereas let's say I know Elasticsearch used to use a replication protocol which was very fault prone, and that came out in the Jepsen test.
I'd like to thank you very much. We will have a Q&A at 2:40 with all of this morning's database speakers before we move on to machine language topics, or machine learning topics. Gosh, I'm at the wrong conference. Before you guys go out, I have a question for you. I need some data, so I'm going to take a poll, a show of hands. Is it too dark in here for anybody who's taking notes? Raise your hands. Okay, that's like a third. Are you comfortable with the temperature? Yes? Okay, cool. Thank you. We'll make sure that we get some lights on, but not too many lights on in the afternoon sessions. Thanks for your feedback. Enjoy your lunch.
Hello? Yeah, it's fine.
Ladies and gentlemen, welcome back from lunch. And I hope you are enjoying our new dimly yet brightly in the back lit auditorium. We listened to your feedback and now you can take notes. Our next session is a question and answer session, and based on how many people in this room, I think we're going to have a lot of questions. For the 4 speakers who came this morning, I'd like to invite them to the stage now. Vijay, Srini, Raghunath, and Dharma, are you here? Ah, there you are. Mic runners, are you ready? Now, it's a 20-minute session, so if you guys want to stand, that's fine. If you want to sit, you can dangle your legs off the stage, whatever is comfortable for you. Who would like to ask the first question? Hands? Anyone?
We've probably seen. Okay, right. Need to not sit on my mic.
Hi, so here's the first question, yeah. So this is for Reku, and it was a great talk. You talked about Polyglot and you showed the architecture of how like Aadhaar is storing stuff, right, in different databases. So is there one copy or there is always a transformation and it's ingested into a different database and a different, I mean you require more space for storing the data?
So basically, some of the raw data is just a single copy, moves across at least 2 of the layers, right, between HDFS and NFS. But over time, there are extracts of it stored in the different layers, right? The Aadhaar generated record, which has the demographic details, sits in MySQL, but the raw data is there in the NFS layer. Right?
So it's transformed and then sent
Yes,
up, but ultimately
extract.
there's just one copy maintained.
The raw data is a single copy, but we have extracts transformed, if you may, and those get stored in the other layers.
Okay. Any problems? So this is the second question. So any problems with the backup of these data stored in these databases? And this is for actually all of you. Backup and restore.
In principle, I'll talk of more of end user, and maybe the database creators can talk in more detail. But few things that we did look at was protecting against any kind of a data loss. So the minimal you can do is, in data stores, if you see, they always follow practices like checksumming data, keeping multiple copies of that, and different ways of making sure that there is no data loss. I think for us, that was one of the main
concerns that we had, saying that if you have to keep the raw data for 7 years, how do we store it in such a way that A, it is not, you protect against bit rot, any kind of data loss, and how do you effectively make it usable?
Adding to that question, so you have the data. For Cosmos DB, I talked about replication. So it's a highly available system. We have 4 replicas of every partition in every region. Beyond that, we take periodic snapshots, and we keep a backup chain. So in case if you have an oops delete, you accidentally deleted a table, you can restore it based on however long the backup chain is kept.
Yeah, from an are you done? Right, I have a mic, I think. Can you hear me? Okay. So from an Aerospike point of view, what I've seen, I mean, this was actually a surprise to me maybe like 8 years ago or 7 years ago. I discovered that our customers didn't really take backups. And one of the reasons is in a real-time system, you want the data to be available all the time. So they will have replication within the cluster. They have multiple clusters running in widely distributed data centers. And the real reason to take backups is to ensure that data is not corrupted by an application. Because here is the problem, right? I mean, something like Aerospike or Cosmos DB is going to keep data live throughout the world. As soon as you make a change, it's going to propagate everywhere. And so if your application happens to have a bug, and it's kind of doing like deleting a table, or even worse, it corrupts, puts the wrong value in millions of keys, it'll immediately be reflected all over the world. So you better have a backup to restore your business. That's kind of a good reason to restore it, not for availability, but more for correctness.
Just to add one point, I think raise an interesting question. So more like a point to ponder kind of thing is people could also look at erasure coding kind of techniques in order to minimize the space rather than use full replication, because full replication tends to be wasteful of space. But coding techniques, especially for the backups, not for live data, because live data there are issues, in how do you tackle in the erasure coded systems. But if it is archival data, right? I think that's something people should consider. Yeah. Go ahead.
We do.
Oh yeah?
Yeah,
Nice.
It's a great point. For the backups, the older the snapshots, the better erasure coding.
I used to build an erasure coded based distributed data store for Oracle a few years back.
That's great.
So, yeah, good. Thank you. Go ahead. There's a question there.
It's according to the current conversation. So you have provided a data that is coming into HDFS, and then one copy goes to the NFS for archival on the fly, or if we need to process and transform the data, that is usually done on HDFS, right? It has its own replication, that is a place for transforming the data. So why, how is that ingestion flow done?
So this is related to the Aadhaar, right? Yes, so sorry, I didn't get your question. So if it is, was it like, okay, it's the same copy that moves from HDFS to NFS. So think of it as the NFS being the archive store and the HDFS being the high throughput processing store, if you were to.
Okay, one more question. It's related to the graph databases. So you are currently working related to Janus Graph or Apache TitanDB. So do you have any other insights you can provide regarding the exploration you have done on graph databases? Graph databases.
Yeah, so on graph databases,
It's not clear. I mean, are you looking for general insights into graph databases, or I mean, the question wasn't very clear for us. If you could elaborate, right? What are you looking for in graph databases?
For example, in graph database, for example, the TitanDB over Cassandra, Apache DynamoDB, different storage engine works. The Gremlin query is getting converted to the SQL queries in between. So all the bottlenecks of this graph engine is depend upon the database engines that is built upon. So as per the evaluations you have done, do you have any comments or insights you can share regarding the graph databases you have worked on?
Yeah, that's actually an interesting question. I mean, Aerospike is a key value store largely. Can do hash joins and hash indexing very well. And one of the things we found is And this is not a general purpose thing, but there are certain graph-like operations you can do very well with a key value store, which can work with batch queries, for example, as well as lookups, batch lookups. So we have found that in a limited way. Other than that, there are specific graph databases like Neo4j, for example, which can also be used, which are customized to just graph applications. Mapping a graph application to something like a key value store, which I'm familiar with, comes with some limitations, but there are certain applications which map really very well. Many may or may not.
Yeah, so my question is for Raghu again. So Raghu, just one thought that I had when you were giving the Polyglot databases and information about that. We generally talk in a data lake or a data platform environment as a single source of truth. And when we look at a Polyglot environment, we are looking at different entities holding data at the same time, right? Are we actually going away from the single source of truth concept altogether, or is it like we are looking at single source of truth replicated across?
So, if you go back to the whole 2.0, ACID 2.0 as a paradigm that you want to adopt, right? So there you're making some specific trade-offs, right? And unless you have access to maybe a CockroachDB or probably a Spanner equivalent, where you can think of a single store that can pretty much serve all your needs. And I was just talking to Dharam outside of the conference. I said, what do you guys optimize for? And if Dharam, if I might quote you, right? So I was saying they do extremely well for OLTP, but probably not that well for OLAP because of the way the engine is built. And they build a lot of things on top to allow you to store, let's say even a MongoDB, shift from there to this and so on. Now, when we looked at it, you should also see it in perspective of when these choices were made. I think in 2010 and 2012, our choices were fairly limited in what they offered, right? And there somehow we made the decision to go with the ACID 2.0 property and its implications rather than, who doesn't want a single database that could probably be across the stack for us, right? Be efficient in storage. But today I also know that practically that might not be possible, right? So in that you are making a few trade-offs, and in that the trade-off was, for us it was consistency primarily, but consistency and where we wanted complete correctness of data, we like the Aadhaar master database, we kept it in a relational store because we knew it's durable, it is transactional, and there's no data loss possible and so on. But the data that we had in our, let's say the Solar layer, which is a secondary index for query, we could always recreate it on demand. So that was acceptable for us.
My question is for Dharma. What is the protocol used for transferring data in a document DB cluster, or is it done on REST?
So by default, there is a REST API for all access methods. But additionally, so there is a REST API for queries for CRUD, stored procedures. Then there is a SQL dialect for accessing all of those operations. And then we have MongoDB, Cassandra, Gremlin, those API heads. Those are server-side wire protocol shims on top of the underlying protocol that we have. Does that make sense?
Hi, I'm here. Okay, you talked about the various NoSQL databases, and if you wanted to get a 10-second response for the large-scale databases, if you have to narrow down which one you choose, the reason I'm asking is that, for example, initially we thought like Apache Spark can perform better for the large-scale database. And then we also saw that there is Apache Ignite, which is an in-memory NoSQL database, works on top of the Spark, and it has the Ignite file system also. So what are your thoughts on the Ignite file system? Ignite, Apache Ignite. I think the question is for the sec.
Okay, you put it in a spot here. Firstly, I've not worked with Ignite. Now, second, if you're talking about an in-memory database with 10-second response time?
You mean 10 milliseconds maybe?
Even 10 seconds,
10 milliseconds
you've given us plenty of time. There are a whole lot of choices around.
Are you talking about 10
You
milliseconds?
can read off HDFS, right? You probably read off even NFS if you will. Sorry, but what's your use case?
The use case is that we wanted to have a reporting on a large-scale database with multiple dimensions and data stored. We wanted to have a response for the not more than 10 seconds or not more than.
So why did you pick a key value store? Why do you
Our use case is not a key value store based. So we are not going by a particular dimension. Okay, we wanted to run a SQL engine and we wanted to generate a report. So
is it an analytical use case or is a user sitting on the other side and waiting for a response?
No, is it an analytic use case only that we are aggregating some KPIs and we wanted to generate a report?
Okay, then my follow-up question is why a time limit of 10 seconds? Analytical queries, you should be perfectly comfortable to run it for a few seconds or a few minutes.
Okay. No, on a larger dimensions, like if you have a larger dimensions and we store it for 300 million.
Okay, let me guess. If you have a business user who's going to come and say that I have this whole data warehouse, I want to be able to query on any of those dimensions and get a 10-second response time, probably want to go and talk to him and say that it's a wrong use case.
Okay.
Sorry, but I think for me that any of the analytical queries, anything that where a 10-second response time is acceptable doesn't fall under an interactive query at all, right? And if it doesn't, then the 10-second could very easily extend to a minute. So then your choices are plenty. You don't need, you're not limited by these kind of choices.
Can I add to that a general point? So you talked about Spark, and you talked about Ignite. I'm not familiar with Ignite either, but I'm somewhat familiar with Spark. The limit on Spark is the amount of data that you can store in memory for it to run. Now, you can, one of the things I mentioned in my presentation earlier today is you could then use a join with another database. In this case, the example I used, of course, was the Aerospike join, index join with a bunch of stuff. So there are ways to extend Spark, but you have to look at it in more detail for your use case, just like Raghu was saying. You can't just take Ignite and say, is it going to work from a use case? You got to have to take a little bit deeper than that, is my recommendation.
On this, I'm happy to discuss offline, maybe you can talk.
It's a deeper discussion.
Over here. Good afternoon, guys. This question is to nobody specific in the panel, but it's to the entire panel, and it's more of a philosophical question than a specific question. So if you look at this space, consider columnar data stores or caches or key value use cases or whatever it is, it seems that we have a problem of plenty. There are way too many products. I'm not saying that every product is the same, but there is quite a bit of overlap, right? I want your opinion on, how does it influence the choices? A lot of companies, a lot of developers are new to these technologies. So does it put firms at a risk of making bad choices? Is it always iterative? You have to, go through an iterative cycle of choices and then reach the right one, or or do you see a consolidation happening in this space over the next few years probably?
Go first.
I see for the last 10 years, when in 2010, around 2010 to all the way now, I see in the last decade there's a movement towards more and more consolidation. There's also a movement towards building databases that are designed for the cloud, like Cosmos DB, like Spanner, like DynamoDB. These are optimized for leveraging the properties of the cloud. So consolidation all in terms of database engine designs, such that columnar indexes and row store indexes are a part of the same engine. Full text support is also a part of the same engine. Just like it happened in relational databases, the similar kind of consolidation is going on in so-called multi-model databases in the NoSQL space. Spanner has also proved that you can have ANSI SQL supported on a NoSQL substrate. So you get horizontal scale out, you get global distribution, but you don't have to forego relational model with some fine print and caveats. Cosmos DB has also gone down in that similar direction. So there is definite consolidation, and there are still use cases where you need purpose-built database. There are still lots of use cases where you need general purpose databases. there's also this dimension of whether do you want to run a live site, or do you want to run the ops for a database cluster, or do you want to just use it as a service? So that's another dimension.
One more answer to that question is, just looking at the choices, right? While there are really many, right? There are 130 NoSQL systems today, but the choices are really quite few. If you look at, for example, which are the CA systems, the CP systems versus the, so on, right? You could narrow it down. So essentially the consolidation has happened in terms of concepts already. People are using only a small set of concepts to implement certain things in certain ways. This has already happened. Like he said, right? For example, Spanner uses certain things to realize asset transactions. So you're going to see more of Spanner-like implementations in the near future. And already most NoSQLs implement Paxos kind of algorithms for consensus. So in that sense, consolidation is already there. It's only that there are different choices, but most of them underlying concepts are similar. So it's not that they have 100 different ways of implementing consensus, but there are only 2-3 ways of implementing it. That's it. So I mean, that's another way to look at it.
Thank you very much. Can you believe we've gone through 20 minutes of questions already?
Can I just follow up with that?
No, I'm sorry.
Really?
We're out of time. If you want to follow up with someone, maybe you can talk to them offline. Okay. We do have a schedule to keep.
Oh, I
sorry.
see.
Question and answer sessions could go on forever. This is an amazing topic. Thank you all very much for your talks this morning and your Q&A now. I'd like to remind you all that we do still have dinner tickets available if you want to come bowling with us. Tickets are available at the registration desk. We are also collecting feedback forms. If you have been filling in your feedback form, the container for putting it is right outside the door of the auditorium. And we really do want your feedback because your suggestions make our conferences better. Tell us what you like and don't like, what you want to see, what topics are interesting. We really do want to hear from you. So next up, we have Lochan. You ready? All right. Who's going to lead us in a little bit more movement? Because for the rest of the day, we're not moving in here. We'll be sitting until 6:15.
Yeah, can I? All right, by now you should know what the first step is. Okay, beautiful. By the way, for the guys who have not realized, the first step is to stand up. Okay, how are we doing on energy? Good? Like there, like low, ready to sleep? Awesome. Okay, so hands by your sides until I fix this in my pants. Okay, so I'd rather wear this. Particular problems with this? Okay. Yeah. Okay, so I like to do this anyway. You don't have to follow me, but it sort of puts me in the mood. Okay, so let's see. I'd like you to stretch your hands out in front of you. Okay. No, you don't have to follow me there. I'm just. Okay, so do this. Down. Up. Down. Up. Down. Okay, beautiful. Right, so now let's just hold more tension here. Right? How many of us have issues with our fingers and our hands in general working on the computer? I see 2 hands. Yeah, that's me. Okay, so, cool. So, obviously one of the major casualties of our job is a problem with our hands. Not enough blood going there, not enough toxins being drained, not enough oxygenation. to fix that. Now, make a fist and release. Fist and release. Fist and release. Okay. Now, the other way. Okay. And feel the stretch. See all that's happening here. It's amazing, like just these hands and the tendons and the ligaments. There's so much happening in your hands. One of the things you can do is just to, like, just let your hand dangle, and just by pushing certain tendons here, you see how your fingers move. I find that very fascinating. I don't know about you, but it's like a remote control there. See, something's happening. Yeah. So, if you are fatigued with your hands, I'd like you to try this thing called the Chinese burn. Okay. So basically, what you do is you stick your hand in front of you. Especially this works if you have a tennis elbow and carpal tunnel, all sorts of RSI, repetitive stress injuries. So you basically take your hand and massage it in a circular fashion. Okay. Yeah, and you go down all the way to your wrist. Okay. And at some point you can also stop. And once you stop, you can move your wrist around a little. Okay, and do that in both directions if you can. Okay, nice. The other hand as well. So there's this Ayurvedic remedy called the Murivenna. I don't know if you've heard of it. But to apply that and do this, if you have any pain, believe me, I mean, it doesn't take much time for it to go. Okay? Alright, beautiful. Now, let's get our hips moving. Do you have space, do you think, to do a hip roll? Can you find the space to do it? If you can. So, your feet are like about hip width apart, maybe a little wider, that's cool, but not too much here. And it's not like your head is bobbing, okay? So keep your head steady, okay? And move as far in front or behind as possible, okay? And you can support your back very gently with your hands here, right? Like so. Yeah, you can look very graceful and beautiful doing it as well, if you can. Impress some people. Okay. So you have this done. I guess you can do about maybe 15-20 rotations in each direction. Okay, when you have the time. I wish I could get into more like extreme postures, but we don't have the space for it, so let's just go with what we have. Okay, raise your right hand. Your left hand is on your thigh here at this point. Okay, and I'm basically, as I'm breathing out, I'm going to my left. And I'm reaching for whatever I can reach for with my right hand. And so it's a stretch that I feel. And I should feel the stretch running all the way on my right hand side, going down my body. And the contraction on the other side. And again, let's not forget to breathe, right? It's important. We forget, we hold our breath, but it's really not helpful at all. Okay, left hand up, right hand here. Down, breathing out. Let's just stay here and feel that stretch. And you don't have to go all the way here. It's okay if you're still here. You'll eventually get there. Okay? Stay and breathe. Beautiful. Okay. Sorry? On foot? After foot, well, you're not bobbing about so much, you're not moving your body that vigorously, so it's not bad. And you're not getting into an inverted posture. It's okay. It's okay. I mean, ideally you want to space this maybe at least an hour after food, or maybe an hour and a half, 2, it's good. Yeah, so, right, so that's one. And obviously a lot of us, I can see, do you have time? Okay, 2 minutes, awesome. We have a lot of problems with our eyes. How many of us wear glasses? Virtually everyone here, right? All right, so that is a problem. We might not consider it as a problem, but it is a very big problem. It's a dependency. And we're feeding a big industry doing it, which is good and bad. And we have issues again of migraines and dry eyes and all sorts of issues. So we want to get rid of that dependency. So it helps from time to time to just leave those glasses out. And the body has an innate potential to heal, which we often subdue and suppress. And we have to give the body that chance to heal, even when it comes to our eyes. Every part of us is capable of healing. Okay, we need to let the body do its thing. We talk about machine intelligence and AI. The body has an intelligence that we don't recognize, which is very funny. Okay, so what you can start off with, just for your eyes, if you can fix your gaze at a point in front of you and keep your eyes there, look down, follow me guys, yeah, look down, and basically keep it right there, keep your eyes right there, and move your head around, like so, okay? So here, you're working the muscles of your neck, and also your extraocular muscles, the muscles that control the movement of your eyes, okay? And do it as slowly as possible with deliberation. You must feel some amount of stress, but there's a good stress and a bad stress. We have to learn to recognize that. Okay? And the other direction. Yeah, that point of focus is important. Okay? Alright, the other couple of exercises we can do, so is to imagine a giant clock, okay, and you're basically looking at the numbers. So the clock is all around you, and you're starting with the number 12, going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anti-clockwise, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 12. Okay, now you can rub your hands. And this is a very important exercise, it's called palming. And you place your palm on the socket of your eyes. You touch your eyeballs very gently, okay? And you need to give it some warmth here. And again, as in any exercise, it's important to breathe. And it's time. I shall see you tomorrow. Bye.
Thanks, Lochan. So this afternoon, talks are mostly focused on machine learning. And our first speaker is going to talk about how to make machine learning faster. If you have a really huge data set, it can take a very, very long time to train. So how do you speed it up? You use something called, I love saying this, hyperparameter optimization. That just sounds so good, doesn't it? So by distributing the load, you speed up the learning. And Anand is going to talk about this and other methods. Are you ready? Okay, thank you very much. Half of the day, Harshal has them, we'll be passing them around to you. Please do fill them in. And the second one is, if you want to escape, there's an OTR in room 1 on, hang on a second, which one is it? Interesting problems to solve with data science. So if you're not interested in machine learning, this is your chance to escape. But nobody's escaping. Thank you very much. All right, looks like Anand is ready.
Yeah. Can you hear me? Okay. So, questions? Let's include questions or? Hello, good afternoon. How is everyone doing? Feeling drowsy after food? Okay, so I hope I won't put you to sleep in this talk. So I'm going to talk about distributed machine learning. Before I talk about, let me introduce myself. So my name is Anand. I'm a co-founder of a startup called Data. We're trying to build a data science platform. So we're trying to build a Heroku-like platform where we're trying to abstract out non-data science components so that data scientists can focus on data science. I also run advanced programming courses at People Academy, particularly do Python and advanced Python courses, Bangalore and around India. In my past life, I worked at a company called Stand Life Sciences, where we kind of built machine learning algorithms from scratch. I guess these years we can start pick Python, scikit-learn, or R, and then start doing things pretty quickly, but those days we had to actually start building things from scratch, or write k-means, hierarchy clustering, support equation, solve it yourself. So have done those things there, and then a easy way to do distributed machine learning. So I really love simple interfaces. For example, take programming. I'm a big fan of Python. So print hello world, that's all you need to write hello world program. You can scikit-learn for machine learning. Take any model, fit, do the training, and predict, got prediction out, right? So simple interface. Now, how do you deploy machine learning models? Couldn't really find anything, so built a small tool called Firefly. So what you do is, you take your Python module, and then function name, and say Firefly that, it starts running a RESTful API that you can use it outside. So it's an open source tool open source library that we built recently. And we started looking at distributed machine learning. What's a simple interface to do distributed machine learning? We couldn't really find anything. Okay. So we thought, let's experiment that and then see if we can build something, if it seems something possible to build something like that. So, so we tried some experiments, and this talk is about summary of what are the state-of-the-art tools available to do distributed machine learning, and something about whatever the experiments that we have done. So if you typically look at traditional machine learning workflow, you do data preparation, feature extraction, and you train your models. And part of the training the models, you do something called hyperparameter optimization or a grid search. What you do is you try to find best model through a set of parameters that you specified. So it goes through all the parameters, all the combinations, and tries to give you the best model possible. So it tries to go through all positive combinations and gives you the model with the best performance. This takes a really long time to do, and if you have a large data set, that's what people do, right? So that's that's a cut for programming, but it's the same code compiling as what model is building, right? So that's what people do, right? People stare at screens and wait for them to finish. How do you speed it up? Right? I think it's very important to speed it up so that people do something more productive than staring at screens or doing something like that. So there's a great opportunity here to parallelize grid sets. There are more things that can be parallelized, but grid sets seems to be the low-hanging fruit, because that's you're giving a set of parameters, and then you're trying to build a model for each one of those parameters. So it seems to be the low-hanging fruit to parallelize. So we thought, let's pick this up and see if this can be run on a distributed cluster and see what it takes to do that. So before actually getting to understand how those things work, let's briefly look into what parallelization patterns are there to understand how that things actually work. So there are two kinds of parallelization patterns. One is data parallelism, and other is task parallelism. So when you say data parallelism, this is what it happens. So what you do is you look at, so you have your input data, you slice that data into multiple parts, And then you run the same task concurrently on multiple cores that are distributed way, and then you get an intermediate data, and then you probably run another task in the same way, and then you get the final output data. So what you're getting is here, you have input data, and then there are multiple processes working all doing the same thing with different sets of data. So this is called data parallelism. And there's a couple of examples of that. If you look at the GPU, what it does is it runs the same instruction, but it runs on 100 cores or 1000 cores, whatever. Then each gets a different data. So it's a single instruction, multiple data patterns. So that's a classic example of data parallelism. And if you've ever done parallel programming, there's libraries called OpenMP and MPI. OpenMP is for parallelizing things on an SMP and a computer with multiple cores. MPI is a message passing interface to do the same thing on distributed cluster. If you look at Apache Spark, the ML algorithms are data parallel. So what they do is they take the data, slice it, and then run it on a cluster. If you take MapReduce, the map of MapReduce, what it does is it takes the data, slices that, and then runs it on multiple machines. So that's a data parallel example. Now let's try to understand what is task parallelism here. So when you look at task parallelism, what you do is you have input data or multiple sets of data, and you have different tasks. They can be executed parallel. They can take the same input data or different data, doesn't matter. But they can be run at the same time. So you can use run them on the same machine with multiple processes within a cluster, and then they produce something output. So this is task parallelism. A couple of examples. So grid search is a classic example of task parallelism because you're trying to build a lot of different models. There are different parameters, but each one of is an independent task. And if you ever use a task queue like celery in Python, what it does is you have a queue of tasks to be executed. There are workers, they pick the task and execute it. So if you look at the data parallelism, task parallelism, data parallelism is usually very fine-grained. So you have very small micro tasks. Whereas task parallelism, tasks are usually bigger. So the task parallelism can even have tasks that take minutes or even hours. So now that we know what are the different parallelization patterns, let's try to go back to our grid search and see how do you parallelize grid search. Okay. Now, well, frankly, you really don't have to do much to actually parallelize grid search because grid search has an option, especially how many jobs you want to run, that runs so many workers and actually tries to parallelize that for you. But the limitation is, excuse me, you're limited by a single computer. So, if it has 4 cores, it runs 4 cores, but if you really want to do even more, that doesn't really work. So, is there a way we can actually return multiple computers? That's what we're trying to see if that's possible. Now, why do you really want distributed machine learning? The reason is, if you run machine learning on a cluster or a lot of computers, the advantage you get horizontal scaling. So, let's try to understand this term, horizontal scaling and vertical scaling. So when you say vertical scaling, what you do is you ask for, give me a bigger machine. Want to even scale up, you say, give me even bigger machine. There's a limit on how big a machine you can get. Whereas in horizontal scaling, what you say is, say, give me more machines. You don't say, give me a bigger machine, but you say, I want the same machine, but I want more of them. That's very easy to get. So when you're an organization you're trying to grow up, it's not easy to get a lot more machines than same machine, one machine with very large size. So horizontal scaling is good, and we're trying to see if we can do that for our machine learning. Now, there are already available solutions. So if you look at Apache Spark, it's a very good tool for doing distributed ML. But the problem is, you can't use the tools that you already use. You can't use scikit-learn, for example. You have to use sparse ML libraries. So if you're already experienced with, let's say, scikit-learn or something, you can't translate the same thing to Spark and start learning all things again. There's another library called Dask Continue that's really very interesting library. It supports multiple backends. It supports threaded process or even distributed backends. So it's very flexible computing library. But again, so how do you do distributed computing with Spark or Dask? There are a lot of challenges, right? So the challenge is it requires setting up and managing cluster of computers. It's not a trivial job for a data scientist to do. You need to have an IT team to set up, and then you run something, and then how do you start things on demand and stop on demand, right? So you're kind of very underutilizing resources. You have a cluster set up for you, but you only run it for very few hours in a day, so you really underutilizing those resources. So our question is it really possible to have a simple interface that a data scientist can manage on his own or her own? So we're trying to see if that is possible. So we did some experiments in this. So what we did is we built, as part of our work to simplify data science, or abstract away the data science, non-data science components in the data science workflows, we built a compute platform. So the platform, what it does is, you can say, I want to run this program, and then say, this program I want to run, starts a job in the cluster and then starts running it. You can specify what instance type that you want. You can say that I want to run it on a machine with 8 GB RAM or 16 GB RAM. You can also specify what environment that you want to run it on. You can say I want to run it on Python 3, TensorFlow 1.2 or Python 2.7 scikit-learn. So it will pick the right environment and then runs the job there. Behind the scenes, what it does is it picks an available machine in the cloud, or starts a new one if nothing is available. It runs a Docker container with the appropriate image, expose any ports required. For example, you want to run a notebook, you have to expose and get a URL to access that. It manages shared disk space so that if you're running multiple jobs, you can have shared storage between them, etc. Let's say, for example, you want to run something, a training on 16-core machine. All you have to do is say run job, tell the instance type I want 16-core thing, and then there you go. So it's running on 16-core machine with all 16 cores maxed out and all those processes running there. Okay. So it's a simple abstraction. What you do is run a job and say what instance you want to say, and it runs in there. So we built this already. Now what we're trying to do is, now that we have this infrastructure with us, can we take this and see distributed machine learning on this? So what does it take? Can you build a simple interface to do this? So, so what we've done is first, we built a low-level tool with the familiar Python interface. So Python has a concept called pool. So you can have a pool of threads or pool of processes. So you can do multiprocess.pool, which gives you a pool of threads or processes. And you can submit, you can map job on rate. So for example, let's say you're trying to compute square of 100 numbers or a million numbers. What you can do is you can create a pool and then map, and then gives you results back by running them on that. So what we've done is we're trying to create a distributed pool. So distributed pool n equal to 5, what it does is it creates n jobs in the cluster to start taking the work from this, and then executes that, and then it gives the result back. So this runs on the same compute platform that we have built. Now that we have basic tool to run distributed learning, so what we try to do a scikit integration. So we wrote a small wrapper to provide our own implementation of grid-set-CV. What it does is, it takes, instead of using grid-set-CV from scikit-learn, you use grid-set-CV from the library that we have. That would, what it does, it uses the distributed pool that we have used in the backend, in the slide before, and then starts running jobs on that. So so if you see, we don't have to really do any cluster setup or anything. Just start using it. This code you can run it on a notebook or on a script, etc. So it starts creating the jobs and runs it, and then you get your results back. So the advantage is, I think, is the simplicity. I really like the first slide I said, simple interface are really good, like Python scikit-learn. So try to achieve a very simple interface, and this kind of sure that simple interface is possible. There's no manual setup required because the platform takes care of everything. It works with familiar interface. You can run things from notebook, etc. If you want to really save your costs, you can say run this on spot instances because the platform supports that. So without any additional setup, you can actually reduce your cost by running on AWS spot instances, etc. So I just, so we're really trying to even see if we can extend this to other things. We're looking at things like, if you look at an ensemble model, there are multiple models packed into one. So when you're training something like that, we're trying to see if it's possible to run each of the model independently in the cluster so that you can get even more scalability. We're trying to see if we can extend this to distributed machine learning, not only to scikit-learn. So I think our implementation is kind of, we have proof of concept implementation of trying this thing. I think what we've done is we've got the interface is really right, so it's very simple interface, people can use it. I'm sure that the implementation you have can improve, will improve over time, but I think really got the API really right. And the summary is, so if you look at, so with large data sets, etc., the distributed learning will be more effective than single computer mode because you can scale up as much as you need. And also, if you actually look at the business side, abstracting away the complexity of distributed learning or any data science workflows, infrastructure, etc., will improve time to markets a lot, right? So you don't have to wait for the months to set up a cluster or get everything working together, etc. So, so kind of have a system which abstracts a lot of infrastructure components and lets you do distributed machine learning with very, very simple interface. So that's all I have, and open to questions. Sure. Yes.
Hello. Hi.
Can't see.
This side.
There? Okay.
I don't know.
Yeah.
Hi, this is Paridhi from American Express, and we do have a lot of data to build models on, and this is exact framework that we are also looking at. My question is that when you are doing a modeling on about terabyte of data, you need that distributed machine learning framework to build the model in the first place.
Okay.
The problem is that the accuracy of the model has to be maintained when you are implementing a distributed version of machine learning algorithms. In your version, how do you make sure that Guinea index or precision is always maintained even when you're using distributed ML version?
So let me clarify one thing. See, here we're not really doing anything about machine learning, right? So all we are doing is we are streamlining the infrastructure part. Okay, we're trying to provide a simple implementation, simplifying the infrastructure part. Okay, so the machine learning algorithms, I mean, whether you run the same thing on in a single machine or a cluster, we're not really tweaking any of these algorithms. So you get exactly the same accuracy or performance that you get in a single machine. You get the point? Yeah, so I'll take it offline. Yeah.
Here is one question.
Which side?
Right here on the top.
Okay.
So the question is, I was a little surprised that you did not mention, for example, TensorFlow or Big DL as one of the choices for implementing distributed machine learning. Any specific reason, or why did you just restrict to only Spark and Dash?
No, so the thing is now, as I pointed out, so we were trying to abstract out non-data science components. Okay, we want to give the choice of what algorithm to use to the data scientist. Okay, so we're not really trying to change the way people do data science, but we're trying to see how people can run things fast, etc., without really changing their workflow. So it's a choice is to use TensorFlow or scikit-learn is to the data scientist who is working on. Okay, so and we're trying to start it with scikit-learn. We're trying to extend that to deep learning. So we will probably go and look into TensorFlow after this. Okay, so I think the key thing is we're not really trying to make a choice of what's a good library to use. It's the data scientist who decides what library to use, and we're trying to make it faster with tools that we're building.
Hi.
Thank you very much. I am afraid we do not
One
have
more
time
question.
for any more questions. We
One
have
more.
our next speaker. Sorry.
Excuse me. Hi.
I'm sorry, we are finished with questions.
I think we
we'll
take
have to
questions.
take your questions offline.
I think we take questions offline.
Yeah.
So I'll be hanging around
This is
there
only a
tomorrow.
20-minute talk, so there's not a lot of time for questions. I'm so sorry. Thank you, Nand. That was really interesting.
Thank you.
So our next talk is a 30-minute talk, which also doesn't have a lot of time for questions, but a little bit more. What do you do when the usual open source suspects like Hadoop and Spark don't work for your project? You could go find another one, or you could build something yourself that works better. So Sriram from Indix is here to explain their open source distributed systems toolkit called Suchi. Sriram, thanks. I've just been told that somebody lost an OTP device in the banquet hall. If that was you, please see a member of staff and we'll get it back to you.
That's all. Okay. Hey, able to hear me? Guys at the back. Okay, thank you. Okay. Good evening, guys. This is Sriram. I'm from Index. So I'm a principal engineer at Index. Been here for 5 years. Mostly worked on a major set of problems at Index and kind of working on machine learning problems right now. If I have to kind of put in context what Index does, Index deals with collecting product information and kind of structuring it and providing it to end users. So we kind of crawl the web for product information, e-commerce stores and other affiliate information about products, structure them and then kind of store it in our database, which is Index, and then we serve it to end users. At a high level, Index deals with, I mean, right now we have anywhere close to 900 million to a billion product records. We have close to 2 billion offers, which spans across 50,000 plus brands and 7,000 plus categories. So that's the scale of problem that we deal with. I'm going to just briefly talk about what the pipeline looks like for us, because I need to kind of set this context so that we get into why we build some of this stuff, which we call switching. So the pipeline is at a high level, we kind of crawl HTML pages from the web, and then we have a series of algorithms which involve processing this unstructured HTML content. Is it audible? Yeah. Unstructured HTML content and then processing it through the pipeline, where we kind of stamp each product with a category. We kind of identify the brand of the product using some of machine learning techniques, and then we also kind of try to go deeper into the product and understand what the product is talking about, like more attributes about the product and so on and so forth. That's at a high level what we do with respect to the pipeline. Now, if you look at the pipeline, there are, I mean, of course, throughout the pipeline, some of the common tenets that we have are scale. We just cannot deal with anything less than terabytes, a few terabytes of data. So that's a given for us. And we also need to have check on latency in terms of how we process and respond to user queries. And the user queries are mostly internal, right? So what we end up having is we end up having a few indices, a bunch of indices across the pipeline to kind of serve some of our requests. And that's why I've kind of put down a couple of databases across a few significant places in the pipeline. So some of the common requirements, so to say, from a technical angle for these systems are, I'm talking about both the processing as well as the storage, right? Some of the common properties that we need are, we need to handle scale, hundreds of terabytes of data. We also need to be fault tolerant because we cannot house everything on one box. We are naturally distributed, but that also means we need to be fault tolerant. And on top of this, I mean, we've kind of tried multiple things and we've realized that operations and productions is very, very critical to kind of managing systems, right? And delivering a delightful user experience. So for us, ease of operations is of utmost importance. So given these, right, we kind of went through our own story of finding the sweet spot for us. But I'm going to kind of take a step back and then see how generally a problem like this is being approached outside, anywhere, right? Or how traditionally we have tried to address this problem from building, in terms of building software. So, I mean, you kind of traditionally slap this system into multiple tiers, kind of compartmentalize your problems, and then say that I'm going to kind of manage the application tier separately from the web tier, and then I'm going to have an ORM or something like that that's going to sit on the application tier and talk to my database, which is going to store information and so on and so forth. So, and more often than not, we are very successful with scaling our web tier and an application tier, but I mean, we know the problem always goes back to the place where we touch the disk or our data store, right? So, and from the morning there has been substantial content that has been provided to support this, in the sense that we know that managing data at scale is very, very hard, and building distributed systems is also very hard. So what we're essentially trying to solve at Index, and of course across a lot of places, is trying to scale data systems, which is to scale storage as well as to scale compute, right? With this context, right, let's kind of see this, how the traditional system is going to be like benefited with the set of technologies that we have got in the last 10 years. The rise of key value stores have actually taken away a lot of the problems that the traditional data stores have given us. I mean, some of the pain points, some of the bottlenecks that we have had with the traditional databases have been kind of taken out of context completely by these distributed systems. But in the previous talk on how to pick a database, he clearly pointed out saying that you need to know whether you want to push your computation onto the applications or you want to leave it with the database, right? So some of these calls were trying to force fit a relational model into a key value store, or trying to force fit a key value store into a relational model is not going to help. So when we kind of scale these applications with distributed data stores, more than, I mean, one part is the design part where we kind of come up with different data stores to fit our needs. The other part is actually the place where we start seeing something called as latency, right? So, and this latency starts to kind of become the biggest monster that you end up dealing with. I mean, if you're using HBase, Cassandra, or any other data store at the back, I'm sure almost all of you have managed HBase and Cassandra who have spent a few weeks, nights, burning midnight oil trying to squeeze the hell out of the GC, right? I mean, there is no doubt on that. So you would end up spending a lot of time trying to tweak some of these settings to ensure that your latency between your application and the data store is within the limits, permissible limits, right? So that is a problem that is not going away. And as you scale, throw more data at these systems, this problem is only getting bigger, right? So what we thought is, why not take it head on and try to solve it to some degree, right? So one of the things that we tried is, can we co-locate our compute and the data, right? So if I can co-locate compute and data, then I'm actually killing some part of latency. Of course, because the nature of problem itself is dealing with scale, I won't be able to hold the entire data set in one box. Naturally, what that means is my latency is only reduced to that portion where there is data locality. But that's still better than having nothing, right? So this idea of co-locating compute and data, what that means is we are moving away from this concept of just a data store to a data service, which is a little bit more intelligent than a data store, which doesn't know how to organize your data and keep it for indexes for that matter, and so on and so forth, right? So building this data service, I mean, it seems to solve some of these problems for you, but when you actually go about doing it, there is a lot of complexity that is involved, because just building a distributed system right out of the box from scratch is not easy, and anyone worth their salt will vouch for it, right? So one of the things that we learned is that we need to take this and solve this problem head on, but not every application writer cannot be solving this problem every time, right? So we kind of understood that we need some middle ground for this. So we kind of understood that there is a data service component that is needed, and we tried to find something in the open source world that kind of fits our need. So how many of you here have used HBase? A large portion of you. And how many of you here have known of co-processors? Okay, very few. Okay, cool. So what I want is something like this. I want a data and compute to be co-located, and co-process fits the bill exactly. I don't need to look outside for anything. I have co-processors which are responsible for, which is basically a unit of processing that is going to lie alongside the shard. Any operation that happens on the shard, the processor is going to be triggered, and whatever action I need to perform there, I can get it done. But the problem is, co-process in HBase is an afterthought. Whether we like it or not, it is an afterthought. It is not designed from the ground up. Because think about this, right? I want to actually release a new version of the application, and my data store is actually shared data store. When I'm running a 100-node HBase cluster, and when I have to share this data store with a couple of applications, what kind of call do I take on the co-process that is running there? Should I throw in a new jar, or should I have an application upgrade, or should I have a database upgrade, a data store upgrade? What do I do there, right? So these things are not very well defined. Plus, the semantics around co-processors are not really well understood in terms of failures and in terms of upgrades. So while there is a little bit of a provision for you, the entire design is not set up in such a way that you are going to be able to use it for your production use cases where some of your business critical logic or your code needs to lie there, right? So now with this kind of setting and with no other option, right, we kind of realize that applications need to own scaling. Developers need to be aware of how to handle scale. That's the bare bones of the reality. Now, how do we solve this so that it's easier for all of us, right? So we kind of debated a lot. We tried some of this stuff, and we realized that we couldn't make use of whatever was available, and then we kind of moved on to something that helped us build our own stuff. Along the way, we realized that taking a call on off-the-shelf versus in-house involves a bunch of parameters. And more often than not, it's a question of your expertise and your need. Is there a real need for you to build something and kind of manage it versus using something that's already available, right? And on top of this, given that we are a startup, we are kind of extremely prudent about cost. If there is a way for us to actually shave down our cluster from 20 nodes to 5 nodes, if I'm able to do that with, let's say, a couple of people working on it for a month or two, I would rather do that. Because the cost of managing an external, a bigger infrastructure and constant attention towards it is a lot more in the longer run than just solving the problem head on, right? So with this kind of setting for us, what we realized is most of the problems that we're dealing with respect to distribution lie into one of these buckets, right? So essentially, for you to build a distributed system, you need to solve, or you need to have a hold of these problems. You need to have an idea of how to establish communication between two machines. How do two machines talk to each other? What is the protocol that I'm going to have for this cluster? Am I going to talk HTTP, TCP, or some custom protocol? How am I going to do that? Right? That's the number one problem that you need to solve. On top of that, you also need to understand who are all the guys that are part of the cluster. So if I'm going to bring up 10 nodes, I need to know who's in the cluster right now, who's going out, who's newly added, what data is there in what node, and a bunch of metadata around these guys. And if I have a cluster of 5 or 10 nodes, then naturally the idea is to store partitions of the data across these nodes, right? So what is the strategy for me to partition data? Technically, it's called sharding. So how do you apply this sharding, and how do you apply your queries in such a way that these systems identify the right shard for your query? It could be just one node or multiple nodes depending on how much data it spans across your queries, but how do you really zero in on a bunch of nodes to actually get your work done? On top of this, having a distributed system without replication is pointless. You're basically shooting yourself in the foot by not having replication and managing data properly. So replication is a must for us to actually do anything in a distributed world, right? So with this context, right, we kind of understood that these are the primitives, so to say, that we need to address. And in the last 3 to 4 years, we kind of built two systems that are in production. And we kind of built distributed systems from scratch. These are very simple master-slave architectures that we kind of understood and built from scratch, and they are in production. And as part of the learning from that, we realized that we could pull out these some of these common primitives as abstractions and see if we can reuse them for building newer systems from ground up, right? At the same time, I was also, me and Ashwant, who's the co-author of this project, we kind of stumbled upon something called as ring pop from Uber, which kind of handles some of this stuff for Node and Go. Sorry. So thus, we kind of brought in Suchi, and then we started hacking on it. It was just started off as any other open source project. We spent a couple of weekends on it, trying to get our hands together and then come up with the basic primitives, set up the interfaces for it, and then try to see how to go about building this. So what does Suchi provide you? As an application developer, if you ask me, what is Suchi providing you, right? It provides you basic blocks to establish communication between the nodes in your cluster. It helps you to pick up a routing strategy, something that we have defined, or if you want to define your new routing strategy, you can kind of write it based on interface and then contribute it back. You also get different modes of replication, and you could choose to have different ways in which you can set up your membership. You could have a gossip-based membership, or you could have a static membership where you predefine the set of nodes that are going to be part of the cluster. Right? So these are the basic primitives that we thought would be essential to get any simple distributed system from ground up. and we kind of went with it, right? So let's take each of these primitives and then go a little bit deeper into it to see what kind of things are supported out of the box right now. So as far as communication goes, we kind of support two major paradigms. One is the handle of forward paradigm, which says that any request that I get, I need to know whether I should be handling the request or I should be offloading to someone else who's responsible for that request. So generally, this primitive is this primitive is common when you know that your queries are localized to a node or localized to a bunch of nodes. There is another primitive which is very common in the aggregation, the stats and the aggregation infrastructure pieces, which is the scatter gather primitive, which is basically saying that my data is going to be thrown across a bunch of these nodes because either it spans multiple, it spans over a timeline, or my query is going to actually span across different facets. So I need to hit a large portion of my data, but at the same time I need to be able to run computes on it and get back the results faster. So the scatter gather primitive is something that we support out of the box. So these two are kind of, so the way you would think of this is that you would write your application service, and then you would kind of configure your application with what kind of routing and your application and other set of strategies that you get, right? So we saw communication, which is basically to say that who has what, which node in the cluster has what, right? Now coming to the routing or the sharding part. So what decides what decides the fact that I am responsible for this chunk of data, right? So this is, we kind of started off building this consistent hash string, which would support routing and replication together, because the data structure itself supports it out of the box for you. So we use a simple consistent hash string. It's kind of well understood for a large set of people who are familiar with distributed systems and kind of understand how routing works generally with data systems. So we have consistent hash string out of the box, but if you want a total ordered partitioner or some other form of partitioner or a router, you could, or a metadata-based router or whatever that is, if you're going to build a master slave thing, then you could always plug in your router and then kind of take it from there. The next component or the next primitive that we support is membership. Like I said, you could bootstrap your application saying that these are the 5 nodes that are part of the cluster, and they would understand each other and they would be able to talk to each other. Or you could actually have a little bit more dynamism with respect to your membership, and you could use dynamic membership. We have color coded it. The dynamic membership is under testing. We're using Atomics or Swim. Basically playing with both right now, which uses Raft underneath for consensus. Atomics uses Raft underneath for consensus. So we are kind of moving towards dynamic membership so that it helps a lot of us to kind of get started by not having to do some of this stuff, and it also helps in environments where your machines come up and go down, especially when you have these orchestrated environments like Mesos and Marathon. So that's on membership. As for the replication, I think one of the most critical things with respect to replication is calling it done. You really need to know when it is done. Is it done when you write it locally, or is it done when you made the call to the remote machine, or is it done when the remote machine actually writes it to disk? And at every level you have different trade-offs. Right now what we support is a serialized synchronous replication. What that means is I write to disk, and then if there is another replica, that replica write to disk is successful only, then the entire write is complete, right? So this of course has this overhead of latency for your request, but this is a call that we took because for us redundancy of data is more important than kind of moving towards this eventual consistent model. We also support asynchronous replication. This is again under testing. We don't, right now we are not having the kind of space to test out this mode of replication right now, but hopefully, we will be able to do that and kind of release it. This is kind of an optional thing. It's not part of the standard distributed system, but we realized that for most of our tasks we use state. One way or the other we use state, we rely on state, and across Index we realized that RocksDB is something that we are getting very comfortable with, and the performance and the benefits that we get out of it seems to be much better than the the other data stores, the embedded stores that we use. So we provide support for embedded KV, which is a RocksDB implementation right now. And of course, you can kind of build your own DB abstraction underneath. Right? So at a high level, these are the various primitives and the support that you get from Suchi. Now, all this is fine. How do I get started? Right? So, I spoke about the communication layer, and I don't know if I kind of touched on it a little bit more deeply. So, we use gRPC for communication. How many of you are aware of gRPC? Okay, that's good. Thank you. So, gRPC uses protobuf underneath. You could define your messages in protobuf, and you can write your service stubs specs in protobuf. You get the generated stubs. All as an application developer you need to do is fill in those stubs with whatever business logic you need, and then wire it into the Suchi's server abstraction. So the server abstraction comes up with a default routing strategy and a replication strategy, and your services are wired up. That way, when you bootstrap your service, you know that who are the peers and what are the services or the functionalities that you're supporting. So when I say a service, you're basically talking of a function. Right? So yeah, I'm going to just, the server abstraction basically wraps up your membership, your router, and your replication. That's pretty much your server abstraction. And each of these is again pluggable. You could implement your own of all of these, right? So this is what we kind of came up with, and with this set of abstractions, we were able to accomplish a bunch of things that at least a couple of systems are running in production with this set of abstractions, and we realized that it's kind of flexible enough for us to kind of work with it, right? Suchi at Index. So what we have is we have two systems which are in production, which are handling live traffic. We have an HTML archiver which is responsible for doing some compute on top of the HTMLs that we receive and index them internally, provide time series based queries on it, and provide pointed lookups on it. So this we are able to do. This is a write-heavy system. Every payload is close to, I would say 300 to 400 KB uncompressed. If you compress it, it's different. So so that's a write payload that is taking, and we have a 5 to 7 node cluster, if I remember right, handling close to terabytes of data, handling hundreds of transactions per second just on writes. On the read side, we have actually built internal MapReduce adapters which we use to scan from this index. And we also built a real-time stats aggregation system based on Suchi. What this meant was we were able to push stats live and get these roll-ups done with this system. So my favorite implementation for Suchi has been the stats, because it kind of captures the essence of doing computes as well as storing data internally, having localized data as well as doing distributed processing for your stats. And we use scatter-gather primitives wherever we need within Suchi to actually roll out the compute across multiple nodes, crunch the numbers, whatever we want there, get localized results, and the guy who actually initially received the request does one more round of processing and pushes it out. So we have kind of set up this system in production, and I think 2 teams at Index internally are pushing stats to this infrastructure right now. And we haven't tested it out exhaustively to understand if it's able to handle millions of events or not, but for whatever the scale, roughly 50 to 100 million events we are able to handle per day. That's something that I know, but how much it can take, we haven't tested. So that's on that. The third system that is being kind of built, that is in progress, we're kind of testing it out in a smaller environment and all that, is our real-time scheduler, which involves rescheduling of URLs dynamically, which also involves data local operations plus data storage plus a global view of the index. So this is something that we are kind of in the work. It's work in progress. It's going to be, a couple of months it will be in production. So that's pretty much what Suchi provides you. I'll actually show you some code that will help you understand, let's say, how simple it is to kind of get started with a distributed system. So yeah. So this is the proto definition that I spoke about. Are you guys able to see it in the back? Is it visible now? Okay. Okay. Better? Okay. So, I mean, this is basically a service definition that I spoke about. You kind of define your service you as a product of service spec. I kind of define a read service which basically gets, I mean, it passes in a GET request and then it gets back a GET response. And you've defined how the GET request looks like. This is just a example of a simple distributed key value store. Right? So, and the basic operations that are supported are get and put. Right? Now, if I have to actually go to the service implementation, which is the read service, you get some of these, I mean, your implementation of get actually gives you a response observer that is the gRPC implementation of the stream from which you got the, so you kind of use the get request, the message that you get as part of your request, and then use the stream response instance that you get to send back a response once you're done with your local processing. Right? Similar is the case with put request. In this case, we are actually storing the data into a data store. And the cool part is with your, I mean, with this, just your two read and write servers, I mean, the service definitions. What you have is you've basically built up a distributed server by just doing this, right? So I create a server abstraction with the netty server, which is basically the transport. I'm kind of defining the routing for the read service using the routing strategy. In this case, it's a consistent hash ring. And I'm defining that I need to do parallel replication. And we've also added a scan service and an aggregate service. It's just a demo. But essentially, you kind of, for every service, you can define your router, and then things could go from there. So that's pretty much on how to get your basic distributed service going with Suchi. Any questions?
We have about 2 minutes for questions, so there's probably time for one. If someone has a question, please raise your hand, and we'll get you a microphone. Do I see a hand? Aha, I see a hand right up here. You can have my microphone.
So Sriram, I can relate to some of the capabilities which obviously you've done good amount of deep work on that, right? I think today when I look at this, I would place it similar to what I see in Zookeeper as a set of capabilities. But somebody went and defined a set of recipes that you can build on top. Right? What I think would help for Suchi is to maybe define a bunch of recipes so that to see if someone is trying to build distributed infrastructure, what are the kind of systems that this would actually be more suitable for? So for me right now, you don't have to answer that now, but I'm finding it hard to figure out. So obviously you used it very effectively in index, but outside of index, if someone were to use it, what would that be for? What class of problems? So maybe those recipes would help.
We actually made some documentation on that. I would, the distributed key value store is a very vanilla example of what we could do. We have also, I mean, we could actually go deeper into this and then kind of talk about what are the various scenarios where, or use cases in the real world that we could apply or build Suchi with. One of the things is just a distributed key value store. The other thing is a distributed stats aggregation system. If you had a requirement like this, you could probably use Suchi. So we have kind of put up a couple of recipes, but we would kind of definitely add more to it and then see if it kind of caters to a wider audience. Thank you.
Thank you, Sriram, for the interesting talk and for creating Suchi.
Thank you.
I'd like to make one final call for flash talks. If you're interested in giving a flash talk today, 5-minute talk, they are starting at 5:10, and you need to give your name, phone number, and the topic of your talk to this man. Come down and do that right now. Also, if you did not already turn in this morning's feedback forms, the feedback form bucket is here. I heard that a lot of you did not accept the afternoon feedback forms. If you want them, come get them from me. If you don't want them, we still want you to have them. So we've got a bit of a quandary. However, you will receive an email that gives you a link to the online version. If you want to be truly anonymous, though, fill in that paper one, because we don't recognize your handwriting. And it is now time for tea break. We will be back here at 4:30 with another talk on machine learning.
No audio.
that got everybody's attention, didn't it? Before we start our next speaker, of course, there are some announcements. If you're coming to the dinner tonight, you'll need to have your badge with you. So bring this. Also, tomorrow morning, when you come, if you're coming for day 2, you will need to check in, which means go to the registration desk and let them scan your badge, which means you need to bring your badge in the morning. We will not be issuing fresh badges. And after this talk, we will have an off-the-record session in this room, which is a little different than our regular talks because you'll get to be doing the talking. I'll tell you more about that when it comes. So if you understand the concept of machine learning, but you're not really sure what to do with it, Raman's going to talk about how to make the leap from practice to production. He's on the data science team at Semantics 3. A warm round of applause for our next speaker.
Yep, so break it. Hopefully it works, yeah. Okay, so thanks for putting up with that. Let's get started. So as it says, my name is Ramana, and I'm here to talk to you about my own experiences in practicing machine learning and how we eventually productionized it at Semantics 3. So I'll just give you a short introduction to Semantics 3. I promise this will be the only slide which mentions it. But what we do is we help e-commerce focused companies. We provide a lot of data solutions, intelligence solutions, and some of those are just there. So we do automated categorization from text to different categories. We do a lot of NLP problems where we want to parse the description present and get out structured data as much as possible. We also do a lot more, like unsupervised extraction, product matching. We also have very talented distributed crawling engineers, one of them is also here, where we help try to index as much as possible. So that's about Semantics 3, but let's get started to the talk, right? So all of you might have heard about it, it's happening, right? So the whole machine learning revolution, people are talking about democratizing AI. So if you have the buzzword bingo sheets, that's one word for this conference. So let's go ahead. You might recognize this picture or you might not. The clue is at the edge. So these are the TPUs or tensor flow processing units, as Google likes to call them. And this is the AlphaGo system, which was used to beat Lee Sedol. So this is like the future which is going to replace us. Of course, this is from ImageNet, where the most recent results for a few years seem to be doing better than human level accuracy rates. So images are being classified by robots much better than many of us here. Google never wants to be left out. This was from their I/O, where they had automated learning throughout all their systems. So you literally point your camera and then Google Lens figures out all the information that you're seeing. And Amazon, not wanting to be left behind, has its own personal, okay, that's the wrong picture, has its own personal assistant, the Alexa, which of course is entering all the homes, and then the data-powered revolution is here. And all of this is happening, and then the next day, you go to the office, and then you talk about all of these breakthroughs. And then your CEO or your board comes to you, and then they say, where are the applications? You are my data scientist, right? So why don't you go ahead and build all these systems for me? And then you try, and then you fail. You try, and then you fail. Because every time you see all of these fancy breakthroughs, there seems to be this gap which sort of jumps, which you need to cross and which you need to jump to make these applications a reality. And that's something which most of us face, or at least I faced a lot at the start. And let's just go through it. So this is sort of like a journey of how everything turned out the way it is. So there are problems about. When you start off, you start hearing all these hard problems. You face all these hard problems you need to solve. People talk about pre-processing your data, training. So which models do you choose? How do you start building them out? Do you choose this framework? Do you choose another framework? How do you scale it out? We've had a number of talks here, even distributed systems, distributed machine learning. all of these ideas of how you take these models and then you scale them out for the next billion users. And delivery, you always are interested in your users, so how do you reach them carefully? So whenever you start off as a project, you see all of these problems. And then on that note, I have like some bad news and some good news, right? So the bad news is that all the companies claim to be unique. They claim to be a special snowflake. The bad news is that you're not. I don't think that you're that unique, that your problems are so hard. But again, flip it around, I think that's also the good news, right? Many companies end up facing the same problems, and then most of them have worked out all of these solutions independent of each other, pretty much duplicating their effort. So that's sort of like the silver lining, which we really need to bring about and start discussing, so that all these problems which have been solved over the years really need to be shared. And this brings me to a story also. So a few weeks back, some of my friends drilled this idea into my brain that there's a mountain out there, we need to climb it. So, and then I get into this, and then this is what, halfway, 3 days later, I find myself like staring up this peak. It's full of sand, you slip every 2 feet. And then I'm like thinking, what have I gotten myself into? This seems like a really hard problem to solve. And then this other guy on my expedition, he just taps me on the back, and then he says, look back for a bit. And then, yeah, this was the view. At that point, I was like, okay, maybe it's worth it. So even when you start off, you see all of these hard problems that you need to solve. But then looking back, it's always very, very beautiful. And that's sort of the point here also. Not to just look forward, but also reminisce on the distance that you've covered so far. And maybe that helps you to motivates you to go further. So this talk is structured in 4 parts. It's not necessarily a play, but let's see if there's some structure to it. Data, and then data, and then data. So good, named it thrice. The whole idea is that you have to start from fundamentals, and then the idea of being a data-powered solution is what needs to be the first thing on your minds. Your first model on how you go about processing your data, or rather building your first training models, how do you think about them? Integration. This is again something which is often overlooked by data scientists, but which I think is a crucial part of the whole ecosystem. You need to be able to talk with your other systems in your company or in your whole model whenever you build it. So integration is something which I also like to focus on. And of course, onwards and upwards, let's just see where do we go from there, or what are the finer points that really need to be discussed. So let's start with data. First there was nothing, and then let there be data, right? For that, we're all computer scientists, so let's start counting from 0. So day 0, what do? You go into the office, and then there's a problem that needs solving. And then you decide, that's when I start collecting my data sources. That's when I start identifying my metrics, which need to be known in order to solve the problem. And then hopefully you just go ahead and solve them. Seems straightforward. But the idea is that this is not the optimal order, at least in our experience. You need to start with the collection first. So it doesn't really matter if you have a realistic problem that you want to solve. The idea is that we start collecting as many metrics as possible within our own company, whether it's within the engineering systems or the customer-facing systems, or just simply because it's there. So just collecting the data and identifying the metrics, I think simplifies the later stages. When you have a problem to solve, you can short-circuit it. You can go from problem and then solution. So identifying your metrics and start collecting them. Because I think by far that's the most effective way to become a rapid prototyping system. So think big, this also ties in because storage is cheap, data is not. In that sense, I mean that the next time you say that you're running out of hard disk space, just go out and buy a few more terabytes of hard disk. They're very cheap. But then realizing that you needed historical data for the last 3 years and you cheaped out on it, that's going to cost you a lot of money. And then there are numerous data sources out there. There's the UCI machine learning repository. There are so many companies which are open sourcing their data. Even today we had the government initiative projects which were discussed, where there are just so many data sources that you really need to think outside the box and be able to identify the relevant sources which might really fit into your problem. And another interesting aspect here, slightly jumping ahead, but it's about pre-trained weights. So some of these companies claim very specific initiatives where they don't want to leak their customer data, but then they end up giving you pre-trained weights which are optimized to solve certain problems. Like in deep learning, one popular approach is that for most of the inception model, you just load it in and then you use that on top of your own images, and sometimes it works fine. So think about pre-trained weights as also like a way of transplanting data which might have been used in some other context.
And speaking of context, most of you will be able to auto-complete this sentence, which starts with garbage in, and then you know what's going to come out. So in that aspect, I think one of the important things to consider is sources of bias, because many times when people build out these data sets and they see that the performance, or we have seen that the performance that we get during training or during our initial releases often is quite different from what we see in production. And that also is a way in which we realize that whether consciously or most probably unconsciously, we as developers, engineers, data scientists, we start identifying patterns and then we start fitting our data collection methods to those patterns. The sources of bias is something we need to look out for, together with two other points, like contextualization and localization. So what do I mean by them? The context is, how was the data collected? So very popularly in psychology studies, the students, first-year psychology students are the data set. So you're only going to be focused, whereas you can't interpret to the general public. Again, that's a problem. Localization, if you want to do consumer behavior in India, you don't want to look at economic history of the Western world or maybe the US, it doesn't matter. And there was a very recent comic also from XKCD, the second time you're seeing it today, I think, where you have data in one end, you're shoveling it into your system, and just keep churning it until you start seeing some relevant results. Hopefully this is not how it's built, but then most of your linear algebra is going to process your data. So once you have these data sets, right, there's a slightly bigger context in which you need to place them. And one of the most important problems that we have seen is about unbalanced data sets. For example, as an e-commerce company, say you're processing credit card transactions, and 99%, even higher percent of the time, the credit card being used is not a fraudulent case. Most of the time, the customer is a legitimate customer, but then you still don't want to let out the fraudsters. So if you build a model which has 99% of one class, you keep guessing that class, you're going to be 99% accurate. Again, that's not very useful because it's just a hard-coded one which keeps coming out of your system. So of course, there are other approaches to fix this. Resampling, I think we just want to talk about like a few. So there's undersampling, where you make sure that the overrepresented class is reduced. There are techniques like SMOTE, which introduce synthetic samples from the existing ones. And of course, you can use variable loss functions. The idea is to provide an overview of all the ways that are possible to actually solve these problems. And of course, like I mentioned, there are a lot of these frameworks which have been publicly announced by a lot of these companies. And there's a saying, right, about giants and shoulders. You just make sure to use them. So there's the text, right? For example, when you start with text, tokenization, stopwords, dictionaries, embedding them in a vector space, encoding them and adding attention framework. Again, all of these are very standard practices which most companies, irrespective of the type of problem that they're solving in a text context, just using these often gives you significant boosts. And being able to incorporate these techniques sort of gives you a playbook. So again, it's not about building your best model from scratch. You start to realize on what are the standard best practices, and I think these things really can translate across the domains. And of course, for images, not wanting to be left out, there are a few techniques as well. You standardize them to 300 by 300 pixels, or you whiten them, you remove the average mean, you divide by the standard deviation, you adjust dimensionality. Again, most of these are applicable across domains, and just being aware of the context in which they were used often gives you significant advantages in how you can actually end up deploying them. Okay, so that was like a quick run through of the data and at least the pre-processing techniques. So how do you go about, once you have this well-curated, perfect data set, right? How do you go about solving it? And then I like to call it pattern recognition. And you might think that this is pattern recognition, where you look at an image and then you process it using your computer, right? But that's not what I'm talking about here. What I like to think of it as humans, we ourselves, need to be able to do problem solving by practice. And what I mean is just being familiar with the number of approaches out there. So when you see something that looks like a duck, squawks like a duck, what do you do with it? So again, it's being able to take a problem, identify the mental framework in which it operates, and then being able to solve it. Machines learn by something called gradient descent, very popularly. And I like to call it something else for humans. Maybe it's someone else who calls it graduate student descent. So it's not gradient descent, it's where a professor employs 50 graduate students to attack the same problem with 50 methods. Or you yourself, you realize one after the other, you spend 6 months attacking it different ways, and then at the end of it, you get a PhD. The graduate student descent is maybe the way students end up learning. This is something I found from scikit-learn, very popular. They call this how to choose the right estimator. I'm not calling it as the best mental model out there, but the idea is that we need to be able to identify these clusters of problems which need to be solved. It doesn't matter if you can't read it, I'll make sure the slides are up at the end and you'll be able to check it out later. Again, it's on scikit-learn, so like there are classification problems, clustering problems, regression, dimensionality reduction. So again, you start with this mental model within yourself. You think, what am I looking at? Is it a model which is computing a number? Is it trying to predict a category? Am I just looking for patterns in the data? And the whole idea is that through experience, you start to realize the models that will end up working in each situation. So model, right? Start here. So let's think of it as a problem, right? So let's say, again, we are focused in e-commerce. So let's say we have this e-commerce website which asks us, how do you end up ranking the products for a visitor? So when someone visits the website, what is the order in which you show the products? One easy way, when they come to us, we build a complex model, we say, feed all your data here, and then we end up solving it. But again, that's not going to work. That's not the way things work, right? The idea I would recommend is that start with a simple heuristic. And what do I mean by heuristic? That's just a fancy way of saying hard-coded rules. So if you want a simple heuristic, you can come up with a way in which you decide, okay, I'm going to rank my products by the number of views that they receive on my website. Maybe that'll get you half the way there. Maybe that'll already start putting the right products in front of people, the products that other people are looking at. And maybe that might end up working for a few months at least for your company. Maybe that helps. And then you realize views are not enough. Maybe I should start sorting my products by the actual orders placed. Maybe that gives me a better conversion. So you go ahead, you build a more complex heuristic, you start hand tuning it. Well, at this point, you're at sort of the slippery slope, so I would suggest don't do that. That's at the point where you start considering actual machine learning models, and then you start building a simple model, and then eventually you start working upwards. So the idea is that not everything needs to be perfect from day one. Maybe you start with a heuristic, and then eventually you start realizing the limitations, and from there you can start taking things forward. So again, driving home the point again, starting simple. Simplify your first objective. And what do I mean by that? So when you ask a startup, like a small company, what's your aim? To make the world a better place, right? Fortunately, we can't optimize that. Unfortunately, feeding that into the model gives us bad answers. So we decide we want to simplify our first objective. We decide we just want to optimize the conversion rate. Maybe that's a small enough number that we can work with. And then once you realize that you have a valid objective in mind, there's this trade-off which people consider initially also, which I'm slightly biased in favor of, where do you need interpretable models? Do you start off with a black box where you feed all the numbers in, and then it spits an answer? There was a talk earlier about explainability in machine learning systems, and then this sort of is related to it. Do you trade off accuracy for explainability? My understanding is that at least initially explainability sort of takes you a long way. Feature engineering is again very linked to being able to explain the results of your model, where you realize which features are leading to the conclusions, and maybe that's really the way to start. And of course, this being fifth elephant, the first 4 elephants are standing on top of a turtle, and then it's turtles all the way down. So ensembles of small models, right? Ensembles of small models are what win the most popular competitions. You go to Kaggle today and then you look at the top results. Most of them are just people who put together 5 models and then tune the respective models, and then they end up winning it. So ensembles seem to have great promise, and most of the times your simple model, when put together, is able to deliver significant results. And this is, okay, so the next topic is slightly related to something which I just very recently learned. Maybe it's useful for you guys as well. It's about model calibration. So let's talk about this graph. It's like an ROC curve. On the x-axis, you have something which you're predicting. Okay? It's a probability between 0 and 1. Say that's the probability of a customer churning over here. And then you end up on the y-axis plotting the number of times that the customer actually churns. You do that multiple times, you see how many times they churn. So say you're predicting 0.2 that the customer is going to churn, but then they end up churning 0.5% of the time. that means your model is sort of an underconfident model. Ideally, the best case is along this center diagonal, but you end up in this sort of model where it's underconfident. Similarly, there's an approach where you end up predicting 0.8, but then it ends up out of the 50 experiments, 25 of them churn, and it's like 50%. So this is something called a Breer score. It's from this book called Super Forecasting. I'm quite sure it's popular in other domains as well, but this is something which you can think about of how your models are calibrated, not just in the context of probabilities of one object, but across all the objects that you predict. Again, looking at some other results, this is again the same graph, and both of these models are 100% accurate. Both of them are on the straight line. But the first one predicts its probabilities within 40 to 60, and it ends up being correct. The second one predicts maybe 0.1 and then 0.9, still ends up being correct. So both of these are well-calibrated models, but you would say that the first one is a cautious system, and then the second one is a decisive system. Both of them have the same accuracy rates, but then these sort of ideas of looking at the model in a bigger picture helps give you a better understanding of how your model is calibrated. So again, autocomplete here, past performance. When you read financial documents, the first thing they say is not indicative of future results. So when you start building your model, the idea is to launch first, move fast, make things, iterate next. And this I mean in a lot of context, especially in relation to the next section on integration. Because when you start building out, the probability that, the system might work on day one, and then eventually the system will begin to degrade because people's behavior tend to change. So the parameters that you trained on might no longer be applicable later on. So the idea is to get a stable pipeline in place, and then later you begin to iterate on the results. Later you begin to see, okay, these things will change eventually. Let's build a complex model. Again, launch first, and then later we figure it out. When you're starting with the model, doesn't matter if it's really simple, as long as it works, push it through. And push it through to this stage about integration and the idea that the ML code that you build is not isolated. And for that I have this great picture. It's from one of Google's published documents which talk about how complex their systems are. So in all my slides, if you see this sort of link over here, eventually if you open the slides, that will link through to the actual content. So that should help you later when I post the link for the slides. And then over here you look at the data collection, feature extraction, data management systems on the left. And then in the middle you have this like very small black box. You can't read it, that just says ML code. So that's effectively the small component that we end up building over all this time. And then eventually you have a lot of these other components. You need to manage your serving infrastructure, you need to manage your monitoring, you need to manage your logging and the process management. The whole point is that you need to look at the big picture with the small ML model. Not necessarily small, but the component in relation to the other parts of your code. It's about an ecosystem which needs to be built, and I think over here at this conference, the idea is to also bring forward this conversation between not just data scientists, but also the engineers, data engineers as they like to call them. It's a whole new field, but the idea is to bring the conversation forward and treat them as engineering problems. Because blindly increasing complexity of the models increases the costs involved. The manpower cost, the time cost, the money cost, every single aspect of your project is going to be delayed if you just focus on optimizing the model. I started off initially focused on the engineering side, so this code at least rings true. It says, do machine learning like the great engineer you are, not like the great machine learning expert. At least I'm not here, or so forth here. So the idea is that you need to identify the strengths to execute a successful product. It's not the aim to publish a research paper which gets another 50% improvement on the state of the art. Again, it's by Martin Zenkovich. It linked to the actual document. It's about plumbing pipelines, the first level of your ecosystem, as I like to think about it. The first level of the ecosystem, the plumbing pipeline, is about your data sources. You need to be able to get a solid pipeline. Again, there are excellent talks over the day which talk about how you stream data, how you use your data stores. Earlier today, how you stream your data from your data stores to your machine learning systems. It's part of the launch, then iterate, because the idea, similar to all other ecological concerns, is to reduce, reuse, and recycle. Try to duplicate the data sources as much as you can between your systems which are used for training and when you eventually do use them in production. or when you use them for serving, in the specific case of making predictions for machine learning systems. The idea is that these plumbing pipelines need to be built not just within your own use or your small Python snippet for processing, but think of it as a framework which needs to be used across multiple projects. Versioning and testing, again, this is speaking as how you develop software problems, right? As how you teach your software system. So whenever a new CTO or a new head of engineering comes in, they throw out the whole system, they curse it, and then they say, let's rewrite everything in the new fancy language today. Is it Node? Maybe something else, I don't know. Yeah. So now they say minimize whole system rewrites. And this, I think, is crucial when you start building the system in your own companies, right? The idea is to build something which can be incrementally updated. Think of it as using Git over your models. Maybe you want a version control system which has the predictions over how many accuracy rates or how many features, how many parameters, maybe the data set over which it was trained, the time during which the data set was generated. The idea is that being able to run a diff command over your models is quite crucial. And this often translates to a lot of other problems like production skew. This is something which you might not have heard of, at least it's not a popular word, but the idea of production skew is how your deployment environment or your whole system which is running starts to deviate in certain ways from the context in which it was trained. So there starts to be this skew between how your system was intended to run and how your system runs. And one of the easiest ways to think about it is about maintaining selected features. And what I mean is that suppose today you're collecting the number of page views on the website. Maybe 5 days later, the UI guy decides that sending back metric information about page views is slowing down the website, so they drop that column, right? Then eventually your system will no longer be able to work with the data. And identifying these sort of features which are no longer applicable is something which people really need to think about when they start building the models. And for that, I like this diagram over here, which talks about how you do deployments. So you have this development system where you work, and then your code sort of flows downstream to your actual deployments. And then the idea is that while code flows in this direction, we need to be able to get data to flow upstream or in the other direction, where whatever you're collecting in production, maybe after some certain anonymization if required and aggregation, you sort of get the data to flow back into your development environments, or at least a snapshot of the data, where code flows downstream and then your data goes back upstream. And this replication of data sources is also tied in with our previous stage, where we really want to duplicate the pre-processing steps involved. So when you start off and start using certain techniques in development, the idea is to try to see if just with scaling out the systems that they run on, that you can use the same techniques in your production deployments. And of course, monitoring is a very popular aspect. Most of us don't care about the DevOps engineers who end up going somewhere else and complaining about their data scientists. But the idea is that monitoring is crucial not just for a performance and uptime point of view, but also in terms of the accuracy of your models and maintaining its own applicability to the problems it's solving. So logging your predictions, and by this I mean not just during your training where you do cross-validation or you do your testing set and then you verify it against your own data set. The idea is to log it across the population that you're serving, and eventually you start to see if the trends that the model reports are consistent with your own expectations. Or maybe the logging eventually also alerts you to failures of your model, which eventually you need to go back and retrain or refix. And there's also another aspect of this, which I like to call A/B testing, but it's also like a finer point to it, where it's better sometimes to hold out your model from touching the users. And what do I mean is that it's connected to something called feedback loops. Say again, going back to the same example, you're ranking the products on your website according to a certain metric, and then it ends up that the first ranked product eventually becomes the most bought product. Now the question is, was your ranking the factor that actually caused the product to become top selling? What if it doesn't matter? You just take your first product and then that eventually becomes the truth. So it's again causation, correlation. So sometimes just ordering the products in a random way, or maybe showing it to a certain portion of the users without touching your model, that helps you build what I like to call a cleaner data set. So this sort of cleaner data set can sometimes really help you identify that these feedback loops can actually overpower the other features that you are looking for. So that's something which eventually the monitoring systems will really help you realize. Okay, so first like a quick run through of everything. Let's talk about onwards and upwards. So this is like the last section. If you're already sleeping, it's just a few minutes to go. Onwards and upwards, and what do I mean by this? It's easy to get bogged down by the minutiae, by the small points, and it's really difficult when you build these systems to look at the application or the purpose for which they were built. And many times having an idea of the bigger picture, whether it's a small company or a big company, it doesn't really matter, but you need to have a bigger idea of what the goals are when you start building these machine learning systems. And this is something which is quite important when you look at production or actual commercial applications instead of just doing it on a training set. And for that, I like this aspect which I call walk by the W's. And by the W's, I just mean the W questions. I mean about questions like who will use the model? Why are you solving this problem? And what will happen? So again, these are the questions which, when provided clearly, when understood really by yourself, really helps you translate how you build your model. Because things like whether the model is going to be used internally by your company or maybe externally by your consumers, that might translate the complexity of the input that you give to your model. Maybe you're solving this problem to optimize a certain aspect of your business. Again, that is the reason that you're solving it. And then what will happen? Like, are you planning on changing the output of your manufacturing sector by a certain number? Or are you planning on optimizing your delivery route or delivery number? Again, all of these help you realize that the features that you select and the assumptions that you make sort of are guided by these W questions, which most people as machine learning practitioners often ignore. But it's quite crucial that people end up seeing it. Okay. And then this ties into the part about business bottom lines. And by this I of course mean the evil business department which is not interested in the purity of the engineering team, but it's about business bottom lines and the decision to launch. So how do you decide that you want to launch your product, right? Again, I believe that this is really a proxy on how you end up visioning your own product or company for the future. The way you launch or the way you update your product is sort of a proxy for where you see your company itself a few years later or maybe even a few months later. For example, metric and objective. This is one thing which is quite common. So when I mentioned that you need to start collecting your metrics, you need to select most probably one of them as your objective. So when you choose to optimize for a certain metric, it might turn out that most probably the other metrics are going to suffer. If you're going to optimize for something like the number of sales, maybe the average sale price is going to go down. Again, this is an idea of how the company itself looks at its own future and how these model updates of which objectives you optimize for are actually a proxy to your business goals. And again, similar to the earlier credit card example, false positives and false negatives. Both of these are bad, but which one is the worst evil, right? Do you want to let the one person who conducted a fraudulent transaction through? Or do you want to put a hassle and break on the thousands of people who just look like they are false positives? Again, these sort of model updates are parameters which end up being a decision which needs to be made together with not just yourself, but an idea of how it affects the business bottom line. So is this the end? Is all of this covered? I don't think so, right? It's about putting all of it together. So when you start with your data, you go about building it, pre-processing it, you construct your own mental model of how it's all structured, you end up integrating it into your systems, and then the idea is that you set yourself up for success in any of these projects by being able to get a workflow in place. And then if you missed most of my talk, it's in 3 words, which is simplify as much as possible, measure your results, whether it's initially or during monitoring, and then be prepared to iterate. I think iteration is the part where you end up really deploying successful systems. So that was my talk for today. It's machine learning from practice to production. If you're interested in the slides, you can scan this QR code. It'll take you back to the talk funnel page. There are a whole bunch of references which I strongly suggest you check out. Most of them are about successful big companies, but of course you can all find it here, and thank you.
We have a few minutes for questions and answers. If anybody has a question, please raise your hand.
Can you hear me? My question is about the fine-tuning of models. So you have a product around catalog creation, right? So the question is essentially, will you consider a signal which is outside of the application to fine-tune your model? For example, if I'm a seller who's already selling on, let's say, Snapdeal, and you are doing that catalog extraction for Flipkart, will you say that this data is pre-processed by Snapdeal, or it is specific to the, like?
Okay, so the question was, I think in maybe two parts. Let me just understand. If you have two different domains, do we share the data from one in the other?
Yeah.
Or
So if the, let's say,
okay, so when it comes to our own systems, we of course have a whole bunch of transfer learning and processing in place, where we end up seeing that data which is used in one context can often significantly boost. So as a data scientist, most often you realize these patterns, and then it does help to take these learnings and then apply them in a different context. But if you look at the raw data itself, we do not support taking data from one store and then giving it to another store. That's something, yeah.
But if the seller is same in that case.
Okay, so looking back at semantics 3 or the specific part that we do deduplication across stores. So if the same product is sold on multiple stores, we treat it as one product. So we make sure that the same product contains the best source of information which is possible, irrespective.
So one step further, have you seen a different behavior response to the user of the same product across different stores? Have you seen the user behaving separately?
I'm not sure if it's really apparent. We don't get that information from the store owners, but I would think that better structured data is definitely better. You've seen the more popular stores, make sure that their data is much more higher quality. Yeah.
Hi, Jay Natarajan from MyMerit. So I just wanted to share, one of the things we see a lot in the fallacies of production is thinking about the model as being trained once and then just set in stone. Have you guys looked at what happens after that with human in the loop? So when things don't pass a confidence threshold, you can pass it to experts, you can feed back edge cases and train further. We see a lot of that as being the key to successful production compared to just thinking about static technology.
Yes, that actually makes perfect sense. The question is, when you start with a model which is say 90% accurate, do you see the performance degrading over time? That's something we see quite regularly. I think each model comes with its own half-life value. And then the idea is to keep monitoring the results as much as possible. You need to have some other loops of verification that ties into the versioning, the testing, and the monitoring parts. So you really need to hold out on a data set and make sure that you're able to collect these data sets from time to time so that the snapshots are not just across segments but also in a temporal dimension.
So also, I think that reinforces the importance of while training, getting a good confidence value. Because if your confidence value is reliable, then you can deploy even with say 90 or 80% as long as you know that that 80% is solid. And then the other 20 you can bounce to an expert or if you try to train it to 97, 98, you might get stuck. And if that 97, 98 confidence is useless, you get stuck.
Yes, so again, those are like clearly valid points. I'm quite sure that you have had these problems over the past. Just being able to train a model to a certain threshold currently, maybe 98, does not guarantee that's going to be 98 2 weeks later. So maybe a trade-off is being able to deploy a good enough model now and then make sure it remains good enough instead of a perfect today and worst one tomorrow. Yep, thank you.
We have time for one last question. So,
My name is Isaac. I'm from Walmart Labs. Two things. One is about the monitoring of the degradation of the model, and the other one you talked about the ensemble, right? Now, here's my question is on how long do you monitor the model versus, say, an existing ensemble. So your use case is like you've got a new model that's come up that's performing very well during the testing phase, and the ensemble is doing okay, but how long do you test one against the other? Because there's a lot of literature out there that says that ensemble will work in the long run. So where do you draw the line?
Again, I think this really depends. So the idea is that when do you know that the model is good enough to replace another? When do you make sure that one of them which is good enough, you can roll it out, right?
One against an ensemble.
One against an ensemble. So my idea was that the ensemble is also treated as one. So when I look at models, again, it's a model below a model below a model. I mean, the idea is that you think of it as a business decision, or maybe you can actually think of it as the A/B testing approach, right? If you end up being able to segment your own user space into maybe statistically significant portions, if you're able to do a hopefully cheap test, not too expensive in terms of what losses it will entail, so that you can test your model against your ensemble, that might be the best way to look at it. How long you do it, there's no straightforward answer, I think. It's about understanding what data you're looking at, whether that data is significantly going to change next year or not. Yeah. Thank you.
Thank you very much. Yeah, I think you had the talk that had the most laughs today. Our next event is an off-the-record one. So we're going to be turning off the live stream, turning off all the video cameras, so that you guys can speak freely. I'd like to call our 5 facilitators up to get their microphones.